Hello, and welcome. I'm glad you're here. Tonight we're going to explore something truly extraordinary: black holes. These are perhaps the most mysterious, most misunderstood, and most beautiful objects in all of existence. They're places where the rules we know seem to bend and break, where time itself slows to a crawl, and where the universe reveals its deepest secrets in the language of gravity and light. But don't worry, we're not here to rush. There's no test at the end, no need to remember everything. Think of this as a slow walk through a cosmic garden, where we'll stop and examine each wonder at our own pace. Some ideas will wash over you like gentle waves, others might spark a moment of curiosity before you drift away. Both are perfectly fine. Before we begin, I'd like to ask, how was your day? Really, take a moment to think about it. Maybe it was long, maybe it was complicated. Maybe it was just one of those days that leaves you tired in ways you can't quite name. Whatever it was, I hope you'll share a bit of it in the comments below. I read them, every single one. It's a small way we stay connected, you and I, across this strange digital space. And if you find comfort in these quiet explorations, if you'd like to join me again for future journeys through the cosmos, please subscribe to the channel. It helps more than you might think, and it means we get to do this again soon. Now let's begin. The term black hole wasn't coined until 1967, even though the concept existed for decades earlier. It's strange to think that something so fundamental to our understanding of the universe didn't have a proper name until relatively recently. For years, physicists fumbled with awkward phrases, frozen stars they called them, or gravitationally collapsed objects. Both names feel almost Victorian in their formality, as if scientists were too polite to call these cosmic titans what they really were: holes in the fabric of space itself. The term black hole came from physicist John Wheeler in 1967, and it stuck immediately. Maybe because it was simple, maybe because it captured something essential about these objects: their darkness, their emptiness, their mystery. Before Wheeler, people knew these things could exist in theory, predicted by Einstein's equations decades earlier, but without the right words, they remained somehow abstract, like trying to describe a colour you've never seen. Language matters in science, perhaps more than we realise. The right name can make an idea feel real, can transform mathematical abstractions into something we can hold in our minds, and black hole, stark, simple, almost poetic, did exactly that. It gave us a way to talk about the impossible, to make comfortable something that should terrify us. And in a way, that's what we're doing here tonight, using words to make friends with the incomprehensible. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from it. Let's sit with this idea for a moment. Nothing can escape. Not matter, not energy, not even light itself. The fastest thing in the universe, the thing that defines our very understanding of speed and distance. Light, which travels at 299,792 kilometers every single second, which crosses the gap between Earth and Moon in just over a second, which lets us see stars that died before our great-grandparents were born. Even light cannot escape a black hole. This is what makes them truly black. It's not that they're painted a dark colour or shrouded in shadow. They're black because they're absence itself. Every photon that ventures too close is captured, pulled inward, never to return. The blackness of a black hole is the blackness of non-existence, of a place where seeing becomes meaningless because there's nothing to see and no light to see it with. And yet, perhaps paradoxically, this absence is created by presence, by gravity so intense it warps space-time itself into a well with no bottom, or rather, a bottom that exists in a place our physics can barely describe. Gravity, which we experience as the gentle tug keeping our feet on the ground, becomes something entirely different near a black hole. It becomes a prison, a trap, a one-way door that leads somewhere we cannot follow, cannot even observe. In a sense, black holes are the universe's way of creating boundaries, of saying beyond this point your rules no longer apply. The boundary surrounding a black hole is called the event horizon, the point of no return, the event horizon. Even the name sounds poetic, doesn't it? It's the line where events stop being observable from the outside world, where the future becomes disconnected from the past in ways that seem almost philosophical. Cross this invisible threshold, and you're committed to the journey inward, no matter how powerful your rocket engines, no matter how desperately you fire them in the opposite direction. What's remarkable is that the event horizon isn't a physical surface. You couldn't touch it, couldn't see it directly. If you were falling toward a black hole, you'd pass through the event horizon without feeling anything special at that exact moment. No wall, no barrier, no sudden change. You might not even know you'd crossed it until you tried to turn back and realized that back no longer existed as a direction. Every path forward leads inward now. Every possible future ends at the singularity at the center. From the outside, though, the event horizon appears frozen. And due to extreme time dilation, something we'll explore more deeply later, anyone watching you fall would see you slow down as you approached, your movements becoming more and more sluggish, your light shifting redder and redder, until you seem to freeze at the boundary forever, a ghostly image that never quite crosses over. But from your perspective, you'd sail right through in finite time, continuing your journey into darkness, while the outside universe races forward through countless ages in what feels like moments. The event horizon is where perspectives diverge completely, where two observers watching the same event see utterly different stories unfold. Black holes come in three main sizes: stellar, intermediate, and supermassive. Not all black holes are created equal. They come in families, if you will, each with its own personality and origin story. The smallest are stellar black holes, born from the violent deaths of massive stars, typically containing between 5 and a few dozen times the mass of our Sun. They're the most common variety, scattered throughout galaxies like cosmic punctuation marks, full stops at the end of stellar lifetimes. Then there are the supermassive black holes, the giants that lurk at the centers of most large galaxies. These monsters can contain millions or even billions of solar masses, their event horizons spanning distances larger than our entire solar system. They're old, ancient perhaps, possibly as old as their host galaxies, and we still don't fully understand how they grew so enormous. And in between, that's where things get interesting. Intermediate mass black holes, containing hundreds to thousands of solar masses, are the mysterious middle children of the black hole family. For years, we weren't sure they existed at all. They were predicted by theory but remained elusive, hiding in places hard to observe. Only recently have gravitational wave detectors begun finding them, revealing a population of black holes that don't fit neatly into our previous categories. The universe, it seems, doesn't care much for our organizational schemes. It creates what it will, in whatever sizes gravity and circumstance allow. And stellar black holes form when massive stars, at least 20 times the mass of the Sun, exhaust their fuel and collapse. Imagine a star, vast and brilliant, fusing hydrogen into helium in its core for millions of years, balancing the inward crush of gravity with the outward pressure of fusion energy. It's a delicate equilibrium, a tug-of-war that most stars maintain for their entire lives. But for the most massive stars, this balance is temporary, almost fleeting in cosmic terms. When such a star exhausts its hydrogen, it doesn't simply fade away like smaller stars do. Instead, it begins fusing heavier elements: helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Each stage burns hotter and faster than the last, a desperate attempt to stave off the inevitable. But iron is the end of the line. Fusing iron consumes energy rather than releasing it, and so the core, now made of iron, has nothing left to burn. The fusion stops. The outward pressure vanishes, and then, in perhaps less than a second, the core collapses. The outer layers, suddenly unsupported, fall inward at 1/4 of the speed of light, rebound off the incompressibly dense core, and explode outward in a supernova that briefly outshines entire galaxies. But the core continues to collapse. If it's massive enough, nothing can stop it. Not neutron degeneracy pressure, not any force known to physics. It collapses past the point where atoms can exist, past the point where even neutrons remain separate entities, collapsing into a singularity surrounded by an event horizon. A black hole is born from violence, from the spectacular death of light itself. Supermassive black holes sit at the centers of most large galaxies, including our own Milky Way. At the heart of our galaxy, 26,000 light-years away in the direction of the constellation Sagittarius, there exists a black hole containing 4 million times the mass of the Sun. We call it Sagittarius a star, and it's remarkably quiet for something so massive. Most of the time, it sits there in the darkness, barely feeding, barely making itself known except through the gravitational influence it exerts on nearby stars. This isn't unusual. Nearly every large galaxy we've observed appears to host a supermassive black hole at its centre, as if there's some cosmic rule that says galaxies and these monsters must grow together. And in a sense, perhaps there is. We're beginning to understand that the mass of a galaxy's central black hole correlates with properties of the galaxy itself, the speed of its stars, the mass of its central bulge. This relationship suggests they evolved together, that the black hole and its galaxy are intimately connected in ways we're still working to understand. Some of these central black holes are anything but quiet. When they feed actively, pulling in vast amounts of gas and dust, they become quasars, objects so luminous they outshine all the stars in their host galaxies combined. These cosmic lighthouses can be seen across the entire observable universe, beacons from the universe's youth when galaxies were still forming and black holes were still growing ravenously. They remind us that black holes, despite their darkness, can be responsible for some of the brightest phenomena in existence. It's one of the many paradoxes that make them so endlessly fascinating. The black hole at the centre of our galaxy is named Sagittarius A, pronounced A star. There's something almost comforting about giving names to these cosmic entities. Sagittarius A, or SGR-A as astronomers often write it, is our supermassive black hole, the one we live with, orbit around at a safe distance along with hundreds of billions of other stars. It's about 4 million times the mass of the Sun, which sounds enormous until you realise that's only about 0.001% of the total mass of our galaxy. A tiny fraction, and yet it sits at the very centre, the gravitational anchor around which everything else revolves. The asterisk in its name actually means something. It denotes that this is a compact radio source. Astronomers detected it first through radio waves, the long wavelength light that passes easily through the dust and gas obscuring the galactic centre. For years they knew something massive was there, could measure its gravity by watching stars whip around it at incredible speeds, but couldn't see it directly. That changed in 2022 when the Event Horizon Telescope captured the first direct image of SGR-A star's shadow, the dark silhouette surrounded by a ring of glowing gas. It was harder to image than the first black hole we photographed, M87 star, despite being much closer, because the material around SGR-A star swirls so quickly that it changes appearance on timescales of minutes. It's like trying to photograph a hyperactive child versus a patient adult. But we did it, and for the first time, humanity looked directly at the shadow of the darkness that sits at our galaxy's heart. Einstein's general theory of relativity, published in 1915, predicted the existence of black holes. Albert Einstein published his general theory of relativity in 1915, fundamentally reshaping our understanding of gravity, space and time. In his vision, gravity wasn't a force in the traditional sense, but rather the curvature of space-time itself caused by the presence of mass and energy. Massive objects bend the fabric of space and time around them, and other objects moving through that curved space follow the contours of that curvature, what we perceive as falling or orbiting. The equations were beautiful, elegant, but also strange. They predicted things that seemed almost too bizarre to be real. And among the strangest predictions, though Einstein didn't immediately recognize it, was that if enough mass compressed into a small enough space, it could curve space-time so severely that it would trap everything, even light, creating what we now call a black hole. Remarkably, Einstein himself was skeptical. He thought nature wouldn't allow such extreme objects to actually exist, that something would prevent their formation. In 1939, he even published a paper arguing against the physical reality of black holes, suggesting they were mathematical curiosities rather than astrophysical realities. It's a humbling reminder that even the greatest minds can underestimate the universe's capacity for extremes. Nature, as it turns out, is far more willing to push boundaries than we are. Einstein gave us the map. It took decades more for us to believe that the territories marked "Here be monsters" were actually real places. The first observational evidence for black holes came in the 1970s from studying X-ray emissions from binary star systems. For decades, black holes remained purely theoretical, mathematical solutions to Einstein's equations that might or might not correspond to anything in the real universe. But in the 1970s, X-ray astronomy, the study of high-energy radiation from space, began to change that. Astronomers started finding peculiar binary star systems where a visible star orbited an invisible companion, and from that orbital dance they could calculate the companion's mass. In some of these systems, the invisible object was too massive to be a white dwarf or a neutron star. And more tellingly, these systems emitted intense X-rays. Radiation created when gas from the visible star spiraled into its companion, heating to millions of degrees in the process. The pattern was unmistakable. Something compact and massive was pulling matter from its neighbour, and that matter was heating to incredible temperatures before vanishing across an event horizon. One of the first and most famous candidates was Cygnus X1, an X-ray source in the constellation Cygnus. The debate about whether it was truly a black hole became so famous that physicists Stephen Hawking and Kip Thorne made a bet about it in 1975. Hawking arguing against black holes, as insurance, he said, in case his life's work proved wrong. Thorne arguing for them. The evidence accumulated over years, and in 1990 Hawking conceded, admitting that Cygnus X1 almost certainly contained a black hole. It was a graceful acknowledgement that the universe is stranger than even our best theories suggest, and that sometimes the monsters in the equations are real. Black holes don't actually suck things in like cosmic vacuums. Their gravity works just like any other massive object. This might be one of the most important things to understand about black holes, and it's also one of the most counterintuitive given how they're often portrayed. Black holes don't reach out and grab things. They don't actively pull matter in from vast distances. Their gravity, strong as it is, follows the same rules as any other massive object's gravity. If you could magically replace the Sun with a black hole of exactly the same mass, 4.6 million trillion kilograms, Earth's orbit wouldn't change at all. We'd continue our yearly journey around this new black hole just as we do around the Sun, at the same distance, the same speed. We'd certainly freeze in the darkness. But we wouldn't spiral inward. The gravity would be identical to what we experience now. Black holes only become truly dangerous if you venture close to them, inside what's called the innermost stable circular orbit, typically a few times the radius of the event horizon. Inside that boundary, yes, you'd begin an inevitable spiral inward, unable to maintain a stable orbit, but that's true of getting close to any extremely compact object. Yeah, the difference with black holes is how compact they are. All that mass compressed into such a small space that you can get far closer to the centre of mass than you ever could with a normal star. So perhaps think of black holes less as cosmic vacuum cleaners and more as cosmic wells, deep, steep wells where if you're careful and stay at a safe distance you can orbit peacefully forever. But lean in too close, peer over the edge, and you'll find there's no climbing back out. When a massive star collapses, it can compress all its matter into a space smaller than a city. Try to picture this if you can. A star that once spanned millions of kilometers, so vast that if you replaced our Sun with it, the star's surface might extend past the orbit of Mars or Jupiter. This enormous furnace of nuclear fusion suddenly finds itself without fuel. And in less time than it takes to read this sentence, all that mass, everything that made up that star, collapses inward. The outer layers fall at speeds approaching a quarter of the speed of light. The core compresses beyond anything we can truly comprehend. Atoms are crushed. The space between atomic nuclei disappears. Even the neutrons themselves, the particles we thought were fundamental building blocks, are compressed beyond their ability to resist. And what remains, what emerges from this catastrophic collapse, is a black hole with an event horizon perhaps 20 or 30 kilometers across. A sphere smaller than Manhattan containing the mass of dozens of suns. It's a compression so extreme that our everyday experience offers no analogies. Imagine taking everything on Earth, every mountain, every ocean, every building, every person, every atom of air, and crushing it all down to the size of a marble. That still wouldn't capture the extremity of what happens when a massive star becomes a black hole. And this transformation, this violent rebirth from stellar giant to cosmic compact, happens in the cosmically brief span of about 1 second. The universe, when it decides to reshape itself, doesn't hesitate. The collapse of a star into a black hole releases more energy in seconds than the Sun will produce in its entire 10 billion year lifetime. Energy is a strange thing to contemplate, especially at cosmic scales. We talk about it casually, the energy in a battery, the energy from a cup of coffee, but when stars die, energy takes on meanings almost impossible to grasp. During the core collapse that creates a black hole, more energy is released in a few seconds than our sun will produce over its entire 10 billion year existence. Not in a year, not in a million years, in its entire lifetime from birth to death. Most of this energy doesn't even emerge as light. It explodes outward in the form of neutrinos, those ghostly particles that barely interact with matter, streaming through the dying star and out into space at nearly the speed of light. In 1987, when a star exploded into a supernova in a nearby galaxy, neutrino detectors here on Earth, deep underground, shielded from everything else, caught a handful of these particles, just a dozen or so neutrinos from the trillions upon trillions that pass through our planet, yet it was enough to confirm that a star 160,000 light-years away had just collapsed into oblivion. The light from that same supernova, the electromagnetic radiation that made it visible to telescopes, carried only about 1% of the total energy released. 1%. The rest vanished into neutrinos and gravitational waves, energy forms we're only now learning to detect and understand. It makes you wonder how many stellar deaths we've missed throughout history. How many black holes formed in silence because we were only watching for light and didn't yet know how to listen for the deeper vibrations of space-time itself. Not all stars become black holes, only those massive enough to overcome the forces that normally prevent total collapse. There's a strange sort of democracy in stellar death. Not every star gets to become a black hole. In fact, most don't. Our sun, for instance, will never achieve that fate. When it exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant, perhaps engulfing Earth's orbit, then gradually shed its outer layers into space, leaving behind a white dwarf, a dense ember about the size of Earth, containing the sun's core mass, slowly cooling over trillions of years. Stars need to be born with at least 20 times the sun's mass to have enough gravitational oomph to collapse into black holes. Anything less, and other forces intervene. Smaller stars become white dwarfs, supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. Larger stars might collapse into neutron stars, where neutron degeneracy pressure provides support, packing the mass of the sun into a sphere the size of a city. But beyond a certain mass threshold, somewhere around 20 to 25 solar masses at birth, no force in nature can stop the collapse. Gravity simply wins. It's as if the universe has decided that below a certain weight class, you get to remain something, retain some structure, some identity. But go big enough, get massive enough, and the universe demands you collapse into pure curvature, into a singularity cloaked by an event horizon. There's something almost poetic about it. The larger stars don't get to rest as corpses. They have to disappear entirely, becoming absences defined only by their gravity. The process of falling into a black hole would appear frozen in time to an outside observer. Here's where black holes start to play tricks with time itself, where the familiar rules we use to make sense of cause and effect begin to bend. Imagine you're watching a friend fall toward a black hole's event horizon. You see them dropping closer and closer, but as they approach that invisible boundary, something strange happens. They appear to slow down, not just a little. They slow down more and more, their movements becoming increasingly sluggish, as if they're swimming through molasses that gets thicker the deeper they go. And the light reflecting off them shifts redder and redder as it climbs out of the deepening gravitational well, stretched to longer wavelengths by the effort. Eventually they seem to freeze entirely, their image stuck just above the event horizon, growing dimmer and redder until they fade from view altogether. But here's the truly mind-bending part. From your friend's perspective, none of this is happening. They don't feel themselves slowing down. To them, they cross the event horizon in a perfectly finite amount of time, maybe seconds or minutes depending on the black hole's size. They continue falling inward, deeper and deeper, while you see them frozen at the boundary forever. Both perspectives are equally real, equally valid. Time itself has become relative in such an extreme way that the word simultaneously loses all meaning. What happens now for them and what happens now for you are completely disconnected concepts. The event horizon doesn't just separate space, it separates time streams, creating divergent realities that can never again share a common present moment. From the perspective of someone falling in, however, they would cross the event horizon in a finite amount of time. So let's be the one falling, shall we? Let's imagine you've decided, for reasons perhaps best left unexplored, to journey into a black hole. You're approaching the event horizon, and from your perspective, everything seems normal. You don't notice any particular boundary or barrier. Space doesn't suddenly feel different. There's no wall, no membrane, no sensation that marks this cosmic point of no return. You cross it. Maybe you check your watch, still ticking. Maybe you check your instruments, still functioning. Everything aboard your spacecraft operates normally. From your frame of reference, only a few minutes or hours might have passed since you began your descent, depending on how fast you fell and from what distance. Here, the event horizon came and went like any other point in space. But if you look back, if you could somehow turn your senses or your eyes toward the universe you left behind, you'd see something extraordinary. The outside universe would appear to speed up. Stars would age before your eyes. Galaxies would evolve. Time itself, compressed by the gravitational effects, would show you the future unfolding at an accelerated pace. In theory, you could watch billions of years pass in what feels like moments, though the practicalities of actually observing this are complicated by light itself struggling to reach you across the extreme curvature. And ahead lies only darkness and the singularity, your inevitable future. The event horizon wasn't the end. It was just the moment when all possible futures collapsed into one. Every path forward now leads to the same destination, and time itself becomes spatial. A dimension you fall through as inevitably as you once fell through space. Supermassive black holes may have formed in the early universe through different mechanisms than stellar collapse. Here's a puzzle that keeps astrophysicists awake at night. We observe supermassive black holes containing billions of solar masses in galaxies that formed less than 1 billion years after the Big Bang. That shouldn't be possible, or at least it shouldn't be easy. If these black holes formed from stellar collapse, they'd need to start with massive stars, wait for those stars to die and become stellar mass black holes, then grow through feeding or mergers. But there simply isn't enough time in the universe's early history for all that to happen and reach the masses we observe. So perhaps they didn't form that way. Perhaps in the dense, chaotic environment of the early universe, enormous clouds of gas, thousands or millions of solar masses worth, collapsed directly into black holes without ever forming stars first. It's called direct collapse, and the conditions have to be just right. The gas has to be hot enough to prevent fragmentation into smaller clumps that would make stars, but cool enough to still collapse under its own gravity. A narrow window, but perhaps one that existed in the universe's youth. Or maybe supermassive black holes grew from seeds that were themselves unusually large. Perhaps intermediate mass black holes formed through exotic processes in the first generation of stars, or even primordial black holes created in the Big Bang itself. We're still piecing together the story, using observations of distant quasars and simulations of the early universe, trying to understand how these monsters grew so large so quickly. It's a reminder that the universe's history still holds mysteries, still presents us with observations that don't quite fit our neat models, still challenges us to imagine new possibilities. Black holes can grow by consuming nearby matter, adding to their mass and expanding their event horizon. Growth, for a black hole, is a messy process. Matter doesn't simply fall straight in. Most of the time it has some angular momentum, some sideways motion. And conservation of angular momentum means it can't just drop directly to the center. Instead, it forms what's called an accretion disk, a swirling disk of gas, dust, and sometimes even stars, spiraling gradually inward like water circling a drain. As this material spirals closer, it heats up through friction and compression. The inner regions of the accretion disk can reach temperatures of millions of degrees, hot enough to emit X-rays and ultraviolet light. Ironically, the process of falling into a black hole, into ultimate darkness, creates some of the brightest objects in the universe. It's almost as if the universe has a sense of dramatic irony. And as matter finally crosses the event horizon, the black hole's mass increases. This isn't a huge amount most of the time. Black holes are surprisingly inefficient eaters, with much of the accretion disk's matter being blown away by radiation pressure and magnetic fields before it can fall in. But over millions or billions of years, even slow feeding adds up. The event horizon expands, Not suddenly, but gradually, its radius growing in proportion to the mass gained. A black hole is never truly finished, never complete. As long as there's matter nearby, it can continue growing, its hunger eternal and patient. When two black holes orbit each other, they gradually spiral inward, eventually merging into a single, larger black hole. Imagine two black holes, and each containing dozens of times the mass of the Sun, orbiting each other across a distance of thousands of kilometers. They dance around their common center of mass, bound together by gravity, whirling through space at speeds that would make our fastest spacecraft look stationary. And as they orbit, something remarkable happens. They lose energy. This energy doesn't disappear. That would violate fundamental laws of physics. Instead, it radiates away as gravitational waves, as ripples in the fabric of space-time itself, propagating outward at the speed of light. These waves are incredibly weak, barely affecting anything they pass through, but they carry energy nonetheless. And as that energy leaves the system, the black hole's orbit gradually decays. They spiral closer and closer together, their orbital period shortening from years to months to days. In the final moments before merger, everything accelerates. The black holes whip around each other dozens or hundreds of times per second, their event horizons distorting, stretching toward each other, and then they touch, merge, their horizons combining into a single, wildly distorted surface that quickly settles into a sphere. The new black hole rings like a struck bell, its surface rippling with overtones that gradually dampen away. And in those final seconds, the merger releases more energy in gravitational waves than all the stars in the visible universe emit as light during the same brief instant. It's one of the most violent events nature can produce, and until 2015, we'd never detected one. The first detected merger of two black holes occurred 1.3 billion light-years away in 2015, September 14th, 2015. Two L-shaped detectors in the United States, one in Louisiana, one in Washington state, simultaneously registered a signal. Or it lasted less than a fifth of a second, a rising chirp that swept upward in frequency and amplitude before cutting off abruptly. That signal had travelled for 1.3 billion years, crossing a distance so vast that when the event occurred, Earth was still in the Precambrian era, its most complex life forms being simple multicellular organisms. What LIGO detected was the merger of two black holes, one about 36 times the Sun's mass, the other about 29 times. They'd been spiralling together for who knows how long, millions of years, perhaps billions, losing energy to gravitational waves until those final moments when they plunged together. In the collision, 3 solar masses worth of energy vanished into gravitational radiation, converted from mass to ripples in space-time according to Einstein's famous equation E = mc². 3 entire suns worth of energy, released in a fraction of a second. The detection changed everything. For the first time, we had direct evidence of gravitational waves confirming a century-old prediction. For the first time, we'd observed black holes merging, seeing the finale of one of the universe's slowest dances. And for the first time, we had a new way of observing the cosmos, not with light, not with particles, but with the vibrations of space-time itself. It was like gaining a new sense, learning to feel the universe in ways we'd never imagined possible. Since then, LIGO and its partner detectors have observed dozens more mergers, each one a message from the violent universe, written in the language of curved space-time. Black holes can theoretically evaporate over time through a process called Hawking radiation. In 1974, Stephen Hawking discovered something that shocked the physics community. Black holes aren't entirely black. Through quantum mechanical effects near the event horizon, they should emit a faint thermal radiation, losing mass in the process. It's called Hawking radiation, and it's one of the most beautiful and strange predictions to emerge from theoretical physics. The mechanism involves quantum fluctuations. Even in empty space, particle-antiparticle pairs constantly pop into existence and annihilate each other, usually so quickly we can never detect them. But near an event horizon, something different can happen. One particle might fall into the black hole while its partner escapes, carrying away energy. To an outside observer, it appears that the black hole has emitted a particle, has radiated. This process is extraordinarily slow for stellar mass black holes. A black hole containing the mass of our Sun would have a temperature about 10 millionths of a degree above absolute zero, far colder than the cosmic microwave background radiation filling space. It would absorb more energy from that background radiation than it would emit as Hawking radiation. Only in the far future, after the universe has expanded and cooled sufficiently, would such black holes begin to actually evaporate, and even then, the timescales are almost incomprehensible. A solar mass black hole would take approximately 10 to the power of 67 years to evaporate completely. That's a 1 followed by 67 zeros, a number so large it makes the current age of the universe seem like an eye blink. In the inconceivably distant future, long after all stars have died and the universe has gone dark and cold, black holes will be the last remaining structures slowly radiating away their mass until they too vanish in final flashes of radiation, leaving behind what? Empty space. Photons. Perhaps something we haven't yet imagined. The universe's final act played out across timescales that dwarf cosmic history itself. Time passes more slowly near a black hole's event horizon compared to regions farther away. Time is not the constant we imagine it to be. We think of it as a river flowing at a steady pace, carrying us all downstream together. But near a black hole, time becomes something stranger, something that flows at different rates depending on where you stand. This isn't science fiction, it's a measured, verified consequence of Einstein's relativity, and near black holes, the effect becomes extreme. Imagine two observers, two friends who synchronize their watches before parting ways. One stays at a safe distance from a black hole, perhaps in orbit far from the event horizon. The other descends closer, hovering just above the point of no return with powerful rockets fighting against gravity's pull. They stay there for what feels like a day by their watch, 24 hours of subjective time, reading books, eating meals, sleeping and waking. Then they return to rejoin their friend. But their friend hasn't experienced a day. Perhaps decades have passed. Perhaps centuries. The closer you get to an event horizon, the more severely time dilates, stretching like taffy until, right at the boundary itself, time from an outside perspective stops entirely. You could hover just above the event horizon for what feels like a week to you, and return to find civilizations have risen and fallen, stars have been born and died, the universe itself has aged millions of years. It's a one-way ticket to the future, if you can somehow escape the gravity well afterward. Time near a black hole doesn't just slow, it becomes negotiable, variable, a dimension that bends as easily as space under the weight of extreme gravity. Some black holes spin at nearly the speed of light, dragging space-time itself along with them. Black holes can spin, and when they do, they don't just rotate like a ball spinning on a table. They drag the fabric of space-time itself around with them, creating what's called frame dragging, or the Lense-Thirring effect. It's as if the black hole is a whirlpool in space-time, and everything near it, matter, light, space itself, gets caught in the current. The fastest spinning black holes rotate at nearly the speed of light at their event horizons. This creates a region called the ergosphere, extending beyond the event horizon, where nothing can remain stationary. Even if you fired your rockets at full power trying to stay still relative to distant stars, you'd be dragged around in the direction of the black hole's spin, not toward it necessarily, but around it, forced to participate in its rotation. Only light itself, travelling at its maximum speed, can move in any direction within the ergosphere. This spinning has practical consequences beyond the theoretical. A rotating black hole is more efficient at powering jets, those enormous beams of particles and radiation that extend for thousands of light years. The spin energy can be extracted through magnetic fields threading the ergosphere, tapping the black hole's rotation and converting it into the kinetic energy of particles moving at nearly light speed. In a sense, the fastest spinning black holes are the universe's most powerful engines, capable of energizing phenomena visible across cosmic distances. And they achieve this not through burning fuel or chemical reactions, but through pure geometry, the rotation of warped space-time itself. The gravitational tidal forces near a black hole would stretch you like taffy, a process colourfully called spaghettification. Let's talk about tides for a moment. On Earth, we experience tides because the moon's gravity pulls slightly harder on the side of Earth facing it than on the side facing away. This difference in gravitational pull, this gradient, causes the oceans to bulge. It's a gentle effect, barely noticeable in our daily lives except when we watch the sea advance and retreat on beaches. Near a black hole, tidal forces become anything but gentle. Imagine falling feet first toward a stellar mass black hole. Your feet, being closer to the singularity than your head, experience stronger gravity. At first, this might feel like a gentle stretching sensation, but as you fall closer, the difference becomes extreme. Your feet are pulled so much harder than your head that you begin to stretch, elongating like a piece of taffy being pulled, and it gets worse. Not only are you stretched lengthwise, but you're also compressed from the sides. The gravitational field pulls everything toward the center, squeezing you narrower as it pulls you longer. The technical term is spaghettification, and while it sounds whimsical, the reality would be anything but. Long before you reach the event horizon of a stellar mass black hole, the tidal forces would overcome the molecular bonds holding your body together. You'd be torn apart at the atomic level, converted from a human into a thin stream of particles spiraling inward. For supermassive black holes, the tidal forces are gentler, their event horizons are larger, and the gravity gradient less steep. You might actually survive crossing the horizon intact. But even then, deeper inside, the tides would eventually win. Gravity always wins in the end. For smaller black holes, spaghettification would happen before you even reach the event horizon. The size of a black hole determines where the tidal forces become lethal. For a stellar mass black hole, say 10 times the Sun's mass, the event horizon has a radius of only about 30 kilometers. The gravitational gradient is incredibly steep at that distance from so much concentrated mass. You'd be torn apart long before crossing the point of no return, perhaps when you were still several hundred kilometers away. But supermassive black holes are different beasts entirely. Consider a black hole containing 1 billion solar masses. Its event horizon would span billions of kilometers, roughly the diameter of our solar system. At such enormous scales, the curvature of space-time near the horizon is actually quite gentle. The tidal forces at the event horizon itself might be no stronger than the tides you experience standing on Earth. This creates a strange possibility. You could cross the event horizon of a supermassive black hole and not immediately realize it. No violent tearing, no sudden pain. You drift across that invisible boundary, committed to your inward journey, still intact and presumably still conscious, able to observe and perhaps contemplate your predicament. Only deeper inside. As you fell toward the singularity and the tidal forces gradually increased, would spaghettification eventually occur? You'd have time. How much would depend on the black hole's mass and spin, but that time would be filled with the knowledge that ahead lies only increasing tides and eventual dissolution. It's somehow both more merciful and more unsettling than instant destruction. Black holes have no hair, a physics term meaning they're characterized by only 3 properties: mass, spin, and electric charge. In physics, hair refers to details, distinguishing features, the unique characteristics that make one object different from another. A person has lots of hair in this metaphorical sense. Their height, eye color, memories, scars, DNA, the exact arrangement of atoms in their body. But black holes, according to the no-hair theorem, have essentially none. Once a black hole forms, almost all information about what fell into it is lost. It doesn't matter whether the black hole formed from the collapse of a pure hydrogen star or a star made of heavier elements. It doesn't matter whether it consumed planets made of rock or ice, whether it ate stars or gas clouds. All that complex information, the entire history of everything that crossed the event horizon, vanishes. What remains are just 3 numbers: the total mass, the total angular momentum, spin, and the total electric charge. This simplicity is both elegant and deeply troubling. It suggests that black holes are the ultimate erasers, destroying information in a way that seems to violate quantum mechanics, which insists that information can never be truly lost. This tension between general relativity and quantum mechanics creates what's called the information paradox, one of the deepest unsolved problems in theoretical physics. Some physicists think the information is somehow encoded on the event horizon itself, preserved in subtle quantum correlations. Others think it escapes in Hawking radiation through mechanisms we don't yet understand. and some think we need an entirely new theory that reconciles gravity and quantum mechanics to resolve the paradox. The question remains open, a reminder that our two best theories of physics, relativity and quantum mechanics, still don't quite speak the same language. A rotating black hole creates a region where you could theoretically extract energy from its spin. Here's a fascinating possibility. You could use a black hole as a battery, extracting energy from its rotation. The process is called the Penrose process, named after physicist Roger Penrose, who discovered it in 1969, and it works within the ergosphere, that region outside the event horizon where space-time itself is dragged around by the black hole's spin. The mechanism is surprisingly elegant. You drop an object into the ergosphere on a carefully calculated trajectory. At just the right moment, you split the object into two pieces. One piece falls into the black hole, crossing the event horizon and vanishing forever. But the other piece, if the trajectories are right, can escape the ergosphere carrying more energy than the original object had. Where does this extra energy come from? From the black hole's rotation. The process slows the black hole's spin ever so slightly, converting rotational energy into kinetic energy of the escaping piece. An advanced civilization could theoretically use this to power itself, dropping matter into a rotating black hole and harvesting the energetic particles that escape. In principle, you could extract up to 29% of a black hole's mass energy this way, far more efficient than nuclear fusion. Over time, you'd slow the black hole's rotation until it stopped spinning entirely, having converted that rotational energy into useful work. It's the ultimate cosmic power plant, and one that could sustain a civilization for trillions of years, long after stars have ceased to shine. Whether any civilization would ever actually build such a thing is another question entirely, but the physics allows it, which is remarkable enough. Light can orbit a black hole at a distance called the photon sphere, circling endlessly without falling in or escaping. At a distance of exactly 1.5 times the event horizon radius for a non-rotating black hole, there exists a strange region called the photon sphere. At this precise distance, the curvature of space-time is such that light can orbit the black hole in circular paths, endlessly circling without spiraling in or escaping outward. It's an unstable orbit, meaning that any slight perturbation would cause the light to either fall inward across the event horizon or escape to infinity. But mathematically, perfectly circular orbits exist there, and this creates some mind-bending scenarios. If you could somehow position yourself at the photon sphere and look to the side, not toward or away from the black hole but tangentially, you could theoretically see the back of your own head. Light leaving the back of your head would travel around the black hole and return to your eyes from the opposite direction. Of course, this is purely theoretical. You couldn't actually hover at the photon sphere without falling in. It's inside the innermost stable orbit for massive objects. And even if you could, the image you'd see wouldn't be clear. You'd see multiple distorted images, light that's wrapped around the black hole different numbers of times, creating a complex layered picture. But the fact that such a region exists, where light itself orbits like a planet around a star, speaks to how profoundly black holes warp the geometry of space. They create regions where the usual rules, light travels in straight lines, orbits are stable, simply don't apply anymore. Black holes are the most efficient batteries in the universe, capable of converting matter to energy better than any other natural process. When matter falls into a black hole through an accretion disk, something remarkable happens. A significant fraction of that matter's rest mass energy gets converted into radiation that escapes the system. For a non-rotating black hole, this efficiency can reach about 6%, meaning 6% of the infalling matter's mass energy becomes light and heat that radiates away before the matter crosses the event horizon. For comparison, nuclear fusion, the process that powers stars, converts only about 0.7% of mass into energy. Hydrogen bombs, our most powerful explosives, achieve similar efficiencies. Even matter-antimatter annihilation, often cited as the ultimate energy source, converts 100% of the mass of the annihilating particles. But you have to create the antimatter first, which requires more energy than you get back. But a rotating black hole is even more impressive. For a black hole spinning at maximum speed, the accretion disk can convert up to 42% of infalling matter into radiated energy. Nearly half of the mass becomes photons and other radiation before disappearing across the event horizon. This is why quasars, supermassive black holes actively feeding in the centres of distant galaxies, can outshine entire galaxies containing hundreds of billions of stars. They're the most efficient engines nature has created, powered not by fusion or chemistry, but by pure gravitational energy, by the warping of space-time itself around rotating singularities. In a very real sense, black holes are the universe's best batteries, and we're only beginning to understand how to observe them discharging. The gravity near a black hole can bend light so severely that you could see multiple distorted images of the same star. Light travelling near a black hole doesn't move in straight lines. It follows geodesics, the curved path through warped space-time, and when the curvature is strong enough, those paths can bend dramatically, creating optical effects that would seem impossible in flat space. Gravitational lensing, we call it, and black holes are among the most powerful lenses in the universe. Imagine a star positioned behind a black hole from your perspective. In flat space, you wouldn't see it. The black hole would block your view, but the black hole's gravity bends light paths around it. Light from the star curves around both sides, some going clockwise around the black hole, some counterclockwise, all of it bending and converging back toward your eyes. You don't see one star, you see a ring called an Einstein ring, a distorted circle of light surrounding the black hole's shadow. And if the alignment isn't perfect, if the star is slightly off to one side, you might see multiple images, one on each side of the black hole, perhaps more if light makes multiple orbits before reaching you. The images would be distorted, stretched, some brightened and some dimmed by the lensing effect. The black hole becomes a cosmic funhouse mirror, creating multiple warped copies of everything behind it. Astronomers use this effect to study black holes and measure their masses. But there's something almost artistic about it too, the way gravity sculpts light, creating beauty from mathematics, turning emptiness into a gallery of distorted reflections. From just outside the event horizon, you could see the entire future history of the universe flash by in moments. Let's return to time dilation one more time, because it creates perhaps the strangest consequence of black hole physics. Imagine you've descended to just above the event horizon of a supermassive black hole. You're hovering there with impossibly powerful rockets. Time for you passes normally. You breathe, think, exist at your usual pace. But relative to the outside universe, your time has slowed almost to a stop. This means that if you look outward, away from the black hole toward the distant cosmos, you see the universe aging at an accelerated rate. Stars evolve quickly through their life cycles. Galaxies rotate visibly. On Earth, if you could somehow see it from here across the light years, civilizations would rise and fall in what seems like moments to you. The farther you descend toward the event horizon, the more extreme this effect becomes. Theoretically, if you could somehow hover at precisely the event horizon itself, which you can't, not really, but imagine it, you would see the entire remaining history of the universe flash by in finite time from your perspective. Billions of years, trillions of years perhaps, compressed into hours or days of your subjective experience. Stars would wink out as they exhausted their fuel. Galaxies would merge and fade. The universe itself would expand and cool, heading toward heat death, all while you watched from your perch at the edge of oblivion. Of course, you couldn't actually share this knowledge with anyone. You couldn't return to report what you'd seen, not if you descended that close to the event horizon. The energy required to escape would be infinite. So you'd be a witness to the universe's end, trapped in a moment that from outside appears frozen, seeing everything while being seen by no one. It's almost poetic in a lonely sort of way, the ultimate perspective from which to observe eternity, purchased at the cost of never being able to leave. Nearly every large galaxy hosts a supermassive black hole at its centre. It took astronomers decades to realise that galaxies and supermassive black holes come as a package deal. At first, the discoveries were scattered, a massive dark object here, an unusually bright galactic core there, but gradually a pattern emerged. Nearly every large galaxy we've examined closely enough appears to harbour a supermassive black hole at its heart, ranging from millions to billions of solar masses. This isn't a coincidence. The relationship is too consistent, too universal to be random. Somehow, galaxies and their central black holes are intimately connected, their fates intertwined across billions of years of cosmic evolution. We're not entirely sure which came first. Did galaxies form and then create black holes? Or did black holes form first and somehow seed galaxy formation around them? Perhaps they grew together, feeding off the same reservoirs of gas and dust, shaping each other through a cosmic feedback loop we're only beginning to understand. What's remarkable is the precision of this relationship. The mass of a galaxy's central black hole correlates closely with properties of the galaxy itself, the mass of its central bulge, the velocity dispersion of its stars. These correlations suggest that despite the black hole containing only a tiny fraction of the galaxy's total mass, often less than 0.1%, it somehow influences the entire galactic structure. Perhaps through the energy released as it feeds, blowing winds that regulate star formation, perhaps through gravitational interactions during the galaxy's youth. The mechanisms are still debated, but the relationship itself is clear. Galaxies and supermassive black holes are partners in cosmic evolution, dancing together through space and time. The mass of a galaxy's central black hole correlates with properties of the galaxy itself, like the speed of its stars. There's a relationship in astrophysics called the M-sigma relation, and it's one of the tightest correlations we've found in the cosmos. It states that the mass of a galaxy's central supermassive black hole is proportional to the velocity dispersion of stars in the galaxy's bulge. Essentially, how fast stars are moving around in the central region. Measure how quickly those stars orbit, and you can predict the black hole's mass with surprising accuracy. Why should this relationship exist? The black hole represents such a tiny fraction of the galaxy's mass that it shouldn't, by naive reasoning, have any influence on stellar motions far from the centre, and yet the correlation persists across galaxies of vastly different sizes and ages. It's as if the black hole somehow knows about the galaxy it lives in, or more accurately, as if they evolved together, each responding to the same cosmic conditions, each influencing the other's growth. Perhaps the answer lies in feedback. When a supermassive black hole feeds actively, it doesn't just grow, it releases enormous amounts of energy. Jets and winds powered by the accretion process can blow gas out of the galaxy's central regions, stopping star formation, heating the remaining gas, fundamentally altering the galaxy's structure. The black hole might be small, but its effects are far-reaching, touching the entire galaxy. And in turn, the galaxy provides the black hole with fuel, with gas to consume and mass to grow. They're locked in a mutual relationship, each shaping the other, their properties becoming correlated through billions of years of coevolution. It's one of the most beautiful examples in astronomy of how the very small and the very large can be deeply, fundamentally connected. Quasars are supermassive black holes actively feeding on enormous amounts of matter, shining brighter than entire galaxies. In the 1960s, astronomers discovered strange objects in the sky that looked like stars through telescopes, but emitted far more energy than any star could. They called them quasi-stellar radio sources, later shortened to quasars, and it took years to understand what they really were. The answer turned out to be both simple and profound. They're supermassive black holes in the centres of distant galaxies, feeding voraciously on surrounding matter. When a supermassive black hole accretes matter at high rates, the infalling material forms a disk that heats to millions of degrees, glowing so brightly it can outshine all the hundreds of billions of stars in its host galaxy combined. From Earth, looking back across billions of light years, we see only that brilliant point of light, the quasar, while the galaxy itself remains too faint to detect. It's as if a single candle were somehow bright enough to make an entire city invisible by comparison. Now, quasars were much more common in the early universe than they are now. When we look at distant galaxies, which because of light's travel time means looking back in cosmic history, we see many more quasars than we do in nearby, more recent galaxies. This tells us something important. Supermassive black holes fed more actively in the universe's youth, when galaxies were still forming and colliding frequently, when gas was more abundant and easier to funnel toward galactic centres. As the universe aged and galaxies settled into more stable configurations, quasar activity declined. The black holes didn't disappear, they're still there, including in our own Milky Way, but they entered a quieter phase, sipping rather than gorging. The age of quasars passed and the universe dimmed, its central engines idling while they wait for the next meal. The most distant quasars we've observed formed less than 1 billion years after the Big Bang. The universe is about 13.8 billion years old, born in the Big Bang, expanding and evolving ever since. When we observe very distant objects, we're looking back in time. The light we see left them billions of years ago. And when we observe the most distant quasars, we're seeing supermassive black holes that existed when the universe was less than 1 billion years old, sometimes as young as 600 or 700 million years after the Big Bang. This presents a profound puzzle. These early quasars contain black holes with masses of billions of suns. But how did they get so large so quickly? If they formed from stellar collapse, they'd start with perhaps tens or hundreds of solar masses. To grow to billions would require consuming enormous amounts of matter in a cosmically brief time. Even if they fed at the maximum theoretical rate, called the Eddington limit, beyond which radiation pressure from the accretion disk blows away incoming material, it's difficult to grow that large that fast. Perhaps they had a head start. Maybe they formed as much more massive objects to begin with. Thousands or even millions of solar masses created through direct collapse of enormous gas clouds in the early universe. Or perhaps they grew through mergers, smaller black holes combining when their host galaxies collided in the dense, crowded environment of the young cosmos. We're still piecing together the answer, using observations from the most powerful telescopes to find these ancient giants and understand their origins. Each discovery pushes our models a little further, challenges our assumptions, reminds us that the universe was doing remarkable things long before Earth existed, long before our solar system formed. Black holes can launch jets of particles at nearly the speed of light, extending for hundreds of thousands of light years. One of the most spectacular phenomena in astrophysics is the relativistic jet, a beam of particles and radiation launched from the vicinity of a black hole, sometimes extending for hundreds of thousands or even millions of light years into intergalactic space. These jets are among the largest structures created by individual objects in the universe, visible across cosmic distances, glowing in radio waves, X-rays, sometimes even visible light. The mechanism involves magnetic fields threading through the accretion disk. As matter spirals inward, it drags magnetic field lines with it, twisting them into complex configurations. These fields can become so twisted and strong that they act like cosmic particle accelerators, channeling some of the infalling matter not inward toward the event horizon, but outward along the black hole's rotation axis. The particles accelerate to nearly the speed of light, these streaming away in narrow beams that pierce through the galaxy and beyond. What's remarkable is the persistence of these jets. They can remain active for millions of years, steadily pumping energy into the surrounding space, creating enormous radio-emitting lobes far from the galaxy itself. The energy involved is almost incomprehensible, equivalent to millions or billions of supernovae released over millions of years. And the source of all this power is ultimately gravitational, the potential energy of matter falling toward the event horizon, converted through magnetic fields into the kinetic energy of particles moving at relativistic speeds. Black holes, despite being objects from which nothing escapes, can be responsible for the most energetic sustained eruptions in the cosmos. It's one of the many paradoxes that make them endlessly fascinating. Some black holes wander through galaxies without a home, ejected by gravitational interactions during galaxy mergers. Not all black holes sit peacefully at galactic centers. Some have been kicked out, sent wandering through interstellar space at high velocities, homeless wanderers drifting through the galaxy. This can happen during galaxy mergers when two supermassive black holes spiral together and merge. The gravitational waves emitted during the final merger aren't always perfectly symmetric. If they're emitted preferentially in one direction, they can impart a recoil kick to the merged black hole, like the recoil you feel when firing a gun. These kicks can be powerful enough to eject the black hole from its galaxy entirely, sending it flying through intergalactic space at speeds of hundreds or even thousands of kilometers per second. More commonly, the kick might not be quite strong enough for complete escape, leaving the black hole on a long eccentric orbit through the galaxy, so far from the center where we'd normally expect to find it. Detecting these rogue black holes is challenging. Without an accretion disk or surrounding stars to mark their position, they're essentially invisible, just mass moving silently through space, detectable only through gravitational effects on nearby objects. Occasionally one might pass through a gas cloud and briefly light up as it accretes material, revealing itself through X-ray emission before fading back into darkness. We think there might be many of these wanderers, orphaned by ancient mergers, drifting through galaxies like ghosts. They're reminders that black holes, despite their gravitational pull, can themselves be victims of gravity's violence, ejected from their homes and left to roam alone through the cosmos. The nearest known black hole to Earth is about 1,500 light-years away. For decades, astronomers searched for the nearest black hole, trying to identify which of our stellar neighbours might harbour one of these dark objects. The answer changes as new discoveries are made, but currently, the nearest confirmed stellar mass black hole appears to be about 1,500 light-years away, a system called Gaia BH1, discovered through careful observation of a Sun-like star's orbital motion around its invisible companion. 1,500 light-years might sound close on cosmic scales, and in a sense it is, that's still within our own galaxy. Yeah, still within what we might consider our cosmic neighbourhood. But in practical terms, it's an immense distance. Light leaving that black hole takes 1,500 years to reach us. If we could somehow travel at the speed of our fastest current spacecraft, the journey would take tens of thousands of years. We're in no danger from it. We'll never feel its gravity. We'll never interact with it in any meaningful way, except through the light we collect from its companion star. And there are likely many more black holes closer that we simply haven't detected yet. Stellar mass black holes that aren't actively accreting matter, that don't have companion stars betraying their presence through orbital motion. These would be essentially invisible, dark objects drifting through space, detectable only if they happen to pass very close to us and lens background stars with their gravity. There might be one 100 light-years away, 50, even closer. We wouldn't know unless we got lucky. Space is vast, black holes are small, and darkness hides well in the dark. Black holes may be factories for creating heavy elements like gold and platinum. The heaviest elements in the periodic table, gold, platinum, uranium, aren't made in ordinary stars. Even the most massive stars fusing elements up to iron in their cores can't create these heavy nuclei. The process requires something more extreme, a CERST environment where neutrons can be rapidly captured by atomic nuclei before they have time to decay, building up heavier and heavier elements through what's called the R process, or rapid neutron capture process. For decades, astronomers suspected that supernovae might provide such conditions, but the models never quite worked. Then, in 2017, we observed something extraordinary. 2 neutron stars spiraling together and merging, an event detected both through gravitational waves and across the electromagnetic spectrum. The observations revealed signatures of heavy element production. The light had colours consistent with atoms of gold, platinum and other precious metals being forged in the merger's aftermath. But what about black holes? When a neutron star spirals into a black hole, similar conditions might exist in the last moments before the neutron star is torn apart and swallowed. The intense tidal forces shred the neutron star, ejecting some of its neutron-rich material into space before the rest crosses the event horizon. In that brief moment, that cosmic catastrophe, heavy elements can be synthesized. And over billions of years, these events might have seeded the universe with gold and platinum, dispersing them into clouds that eventually formed new stars and planets. The gold in your jewellery, the platinum in electronics. Some of it might have been created at the edge of a black hole, forged in gravity's crucible before being scattered to the stellar winds, eventually finding its way to Earth. The combined mass of all stellar black holes in the Milky Way is estimated to be about 100 million solar masses. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Of those, only a small fraction, perhaps 1 in 1,000, were massive enough to end their lives as black holes. That still leaves a substantial population, maybe 100 million individual stellar mass black holes scattered throughout the galaxy, each containing between 5 and a few dozen solar masses. Add them all together, and you get a combined mass of perhaps 100 million times the Sun's mass, all locked away in black holes. It sounds like a lot. And in absolute terms it is. That's a substantial amount of matter compressed into objects we can barely detect. But in the context of the galaxy as a whole, it's almost negligible. The Milky Way's total mass is estimated at around 1 trillion solar masses when you include dark matter, or about 60 billion solar masses in visible matter alone. The black holes represent a tiny fraction of that total, less than 0.2% of the visible matter, and yet they're there. As invisible points of darkness scattered through the spiral arms and the halo, remnants of ancient massive stars waiting patiently for something to wander too close. Most will float through space for billions of years without encountering anything substantial, silent and dark, neither growing nor shrinking appreciably. They're the galaxy's hidden population, far outnumbered by stars but present nonetheless. A dark demographic that shapes our cosmic census in ways we're only beginning to understand. Some galaxies have two supermassive black holes in their centres, orbiting each other as their parent galaxies merge. When two galaxies collide, and collide is perhaps the wrong word since galaxies are mostly empty space, and stars rarely actually hit each other, their central supermassive black holes eventually find each other through gravitational interactions. The galaxies merge. They're gas and stars mixing and settling into a new configuration. But the black holes begin a long dance that can last millions of years. At first they orbit at large separations, perhaps thousands of light years apart, each still embedded in the remnant of its original galactic core. Gradually, dynamical friction, interactions with surrounding stars and gas, causes them to spiral inward, their orbital separation shrinking over time. As they get closer, their orbital period shortens from millions of years to thousands, then hundreds, then less. Eventually they reach a separation where gravitational wave emission becomes significant, and the final phase begins. They spiral together more rapidly now, losing energy to ripples in space-time, until in the final moments they're orbiting each other hundreds of times per second before merging into a single, larger black hole. The gravitational waves from such a merger would be enormously powerful, far stronger than stellar mass black hole mergers, though at lower frequencies that our current detectors can't quite reach. Future space-based gravitational wave observatories should detect these events, giving us a census of supermassive black hole mergers across cosmic history. And somewhere right now, in galaxies we can see through telescopes, these dances are occurring, black holes locked in orbital embrace, and slowly spiraling toward an inevitable merger that might not happen for millions of years, but will happen nonetheless. Gravity is patient, but it always finishes what it starts. In 2019, we captured the first direct image of a black hole's shadow in the galaxy M87, April 10th, 2019. Scientists held press conferences simultaneously around the world to reveal an image that had been decades in the making. It showed a glowing orange ring of light surrounding a dark circle, the shadow of a black hole. Photographed for the first time in human history, not an artist's rendering, not a simulation, but an actual image captured by combining data from radio telescopes scattered across Earth. The black hole resides in the galaxy Messier 87, about 55 million light-years away in the constellation Virgo. The image doesn't show the event horizon itself, that's truly invisible, but rather the photon ring, the region where light orbits the black hole before either escaping or falling in. The dark area in the centre, about 2.5 times larger than the event horizon, is the shadow cast by the black hole against the glowing accretion disk behind it. Creating this image required turning the entire Earth into a telescope. The Event Horizon Telescope project linked radio dishes on 4 continents, from Hawaii to Chile to Antarctica, synchronizing their observations with atomic clocks to create a virtual telescope the size of our planet. Even then, the resolution was just barely sufficient. M87's black hole, despite being enormous, subtends an angle in the sky about the same as seeing a donut on the moon from Earth. The data took years to process, combining petabytes of information, accounting for Earth's rotation, atmospheric effects, instrumental quirks. But when the image finally emerged, it matched predictions from Einstein's equations made a century earlier. We'd not only seen a black hole's shadow, we'd confirmed that our understanding of gravity and spacetime tested in these most extreme conditions still held true. The M87 black hole in that famous image is 6.5 billion times the mass of the Sun. Let's try to grasp this scale for a moment. The Sun contains about 333,000 times the mass of Earth. It's massive enough that more than 1 million Earths could fit inside its volume. And the M87 black hole contains 6.5 billion of them. 6,500,000,000 suns worth of mass compressed into a region that, while enormous by black hole standards, is still smaller than our solar system. The event horizon of this giant has a radius of about 20 billion kilometers, roughly 130 times the distance from Earth to the Sun. If you place this black hole where our Sun sits, its shadow would extend well beyond the orbit of Neptune, swallowing all the planets, and yet. From 55 million light-years away, it appears as just that tiny circle in our telescopes, requiring the combined resolving power of an Earth-sized instrument to image. This black hole likely formed billions of years ago, possibly when the universe was young and has been growing ever since through mergers and accretion. It's currently feeding, pulling in matter that heats and glows as it spirals inward, which is why we can see the bright ring in the image. But it's not feeding particularly actively. This is relatively quiet for a supermassive black hole of its size. When it was younger, when more gas was available, it might have shone as a brilliant quasar, outshining its entire galaxy. Now it's settled into a gentler phase, still massive, still growing, but at a more leisurely pace. Even black holes, it seems, calm down with age. The glowing ring in black hole images isn't the event horizon itself, it's hot gas swirling around it. When you look at those famous black hole images, it's important to understand what you're actually seeing. The darkness in the center isn't the event horizon. It's larger, a shadow cast by the black hole, and the glowing ring isn't matter at the event horizon about to fall in. It's the photon ring, a region where light from the accretion disk gets bent and lensed by gravity, creating a luminous halo around the shadow. The accretion disk itself extends much farther out, and we're seeing light from different parts of it. Some of the light comes from gas orbiting on our side of the black hole, some comes from gas behind the black hole, but gravity bends those light paths up and over or down and under, so we see it too. And some photons orbit the black hole one or more times before reaching us, creating multiple overlapping images compressed into that bright ring. The brightness isn't uniform around the ring. One side appears brighter than the other, and this asymmetry tells us something important. The black hole is rotating, and matter in the accretion disk is moving at a significant fraction of light speed. On the side where matter moves toward us, relativistic beaming makes it appear brighter. On the side where it moves away, the light is dimmed. This brightness difference let astronomers determine which direction the black hole spins. In M87's case, the jet points roughly toward us, and the disk rotates clockwise from our perspective. Every detail in these images carries information, encoded in photons that travelled 55 million years across space to tell us their story. In 2022, we captured our first image of Sagittarius A, the black hole at our galaxy's centre. 3 years after imaging M87, the Event Horizon Telescope team revealed another image, Sagittarius A star, the supermassive black hole at the heart of our own Milky Way galaxy. You might think this would be easier than imaging M87. After all, SGR-A star is only 26,000 light-years away compared to M87's 55 million, over 2,000 times closer. But in practice, it was significantly harder. The problem is timescale. M87's black hole is so massive that matter in its accretion disk takes days or weeks to complete an orbit. The disk's appearance remains relatively stable over the hours needed to observe it, but SGR-A star, despite containing 4 million solar masses, is much smaller. Matter in its accretion disk orbits in minutes, meaning the disk's structure changes even while we're observing it. It's like trying to photograph a fidgeting child with a slow exposure camera versus photographing a patient adult. The solution required new analysis techniques, essentially taking thousands of shorter snapshots and averaging them together to find the underlying structure. The result, revealed in May 2022, shows a familiar glowing ring around a dark shadow, thus remarkably similar in appearance to M87 despite the enormous difference in mass. This similarity is actually expected from relativity. The appearance of a black hole's shadow depends primarily on its spin and viewing angle, not its absolute size. Both images confirmed predictions. Both showed the characteristic photon ring. Both proved that Einstein's century-old equations still work at these extremes. And this one was personal. We were looking at the gravitational anchor of our own galaxy, the massive darkness around which we orbit. Gravitational wave detectors have now observed dozens of black hole mergers. Since that first detection in September 2015, gravitational wave astronomy has matured from a hoped-for possibility to a routine observational technique. LIGO in the United States, joined by Virgo in Italy and CAGRA in Japan, has detected dozens of black hole mergers, along with neutron star mergers and hybrid events where black holes consume neutron stars. Each detection is a story, a cosmic collision that happened millions or billions of years ago, its ripples reaching us only now. We've seen mergers of black holes ranging from a few solar masses to nearly 100 solar masses. We've detected systems where the two merging black holes had similar masses, and systems where one significantly outweighed the other. We've measured spins, tracked how the orbital plane precesses before merger, and begun to understand the population of black holes across the universe. What's remarkable is how quickly this has become normal. When LIGO made its first detection, it was headline news around the world, a Nobel Prize-worthy discovery. Now, detections happen regularly during observing runs, sometimes multiple per week. The detectors turn on, the universe speaks in gravitational waves, and we listen. Each signal teaches us something about black hole formation, stellar evolution, the expansion rate of the universe, the nature of gravity itself. We're still in the early days of this new astronomy, still learning to interpret what we hear, but already we've learned more about black holes from gravitational waves than from decades of electromagnetic observations. The universe has always been singing these gravitational songs. We've simply learned, finally, to hear them. Some black hole mergers have revealed intermediate mass black holes, now filling a gap we weren't sure existed. For years, there was a curious gap in the black hole population. We knew of stellar mass black holes, from a few to a few dozen solar masses, formed from collapsing stars. We knew of supermassive black holes, millions to billions of solar masses sitting at galactic centers. But intermediate mass black holes, from hundreds to hundreds of thousands of solar masses, remained elusive, theoretically possible but observationally rare. Then gravitational wave detectors began finding them. In 2019, LIGO detected a merger that produced a black hole of about 142 solar masses, well into the intermediate mass range. The two merging black holes were themselves surprisingly massive, 85 and 66 solar masses, larger than we expected stellar collapse to produce. This opened questions about how such massive black holes form in the first place. Perhaps they're the product of previous mergers, hierarchical growth where smaller black holes combine, and those combinations combine again, building up through generations. Perhaps they form in dense stellar clusters, where multiple stars collapse simultaneously or in rapid succession. Perhaps some are primordial, created in the early universe through mechanisms we don't fully understand. The detections continue, slowly filling in the population, revealing that intermediate mass black holes exist and might be more common than we thought. Each new discovery refines our models, challenges our assumptions, shows us that the universe creates black holes across a wider range of masses than our theories initially predicted. The gaps in our knowledge are filling, but with each answer come new questions about formation mechanisms, environments, the cosmic history that created these objects. Our X-ray telescopes can watch as matter spirals into black holes, heating to millions of degrees. When matter falls toward a black hole, friction in the accretion disk heats it to extraordinary temperatures, millions of degrees in the inner regions closest to the event horizon. At these temperatures, matter radiates primarily in X-rays, high-energy photons that our eyes can't see, but specialized telescopes can detect. These X-ray observations let us watch, in real time, as black holes feed. The X-ray emission isn't constant. It flickers and varies on timescales from milliseconds to days, reflecting turbulence in the accretion disk, instabilities in the flow of matter, possibly the effects of the black hole's spin on the infalling material. By studying these variations, astronomers can probe regions very close to the event horizon, far too small to image directly even with our best telescopes. So some black holes show quasi-periodic oscillations, regular flickering at specific frequencies, like a cosmic heartbeat. These might be caused by hotspots in the accretion disk, regions of enhanced emission that orbit the black hole and come into view periodically. Or they might reflect fundamental modes of oscillation in the disk itself, the whole structure ringing like a bell. The exact mechanisms are still debated, but what's clear is that X-ray observations give us a window into the dynamic, violent environment just outside the event horizon, letting us study physics and gravitational fields billions of times stronger than Earth's, in conditions we could never replicate in laboratories. Every flicker, every burst, every variation carries encoded information about how matter behaves in gravity's most extreme embrace. We've detected stars orbiting so close to Sagittarius A that they complete an orbit in just 16 years. In the center of our galaxy, astronomers have been tracking stars orbiting Sagittarius A star for decades now, measuring their positions year after year, watching them trace elliptical paths around the invisible massive object. One star in particular, designated S2, or SO-2 in some catalogues, has become a gravitational laboratory. S2 completes a full orbit around SG Ra star in just 16 years. At its closest approach, it comes within about 17 light-hours of the black hole, roughly 120 times the Earth-Sun distance. Incredibly close given the black hole's mass. At that point, it's travelling at about 3% the speed of light, fast enough to experience measurable relativistic effects. In 2018, when S2 made its closest approach, astronomers watched carefully. They measured the star's light spectrum looking for the gravitational redshift, the stretching of light as it climbs out of the black hole's gravitational well. They measured the shape of the orbit, looking for perihelion precessions similar to what Mercury shows around the Sun, but much more extreme. The observations confirmed Einstein's predictions. General relativity, tested in a gravitational field 400 times stronger than Mercury experiences, still worked perfectly. This ongoing experiment turns the galactic centre into a cosmic laboratory. With each orbit, we refine our measurements, test general relativity more precisely, learn more about the black hole's mass and spin. And S2 isn't alone. There are other stars even closer with shorter periods that will provide even better tests in the future. We're using stars as test particles, watching them orbit a black hole with the regularity of clockwork, and in their motion we read the fundamental nature of gravity itself. Some black holes flicker and fluctuate on timescales of minutes, revealing the chaotic environment near the event horizon. Near a black hole, matter doesn't fall in smoothly. The accretion disk is turbulent, threaded with magnetic fields that create instabilities, shot through with shocks and hotspots. And this chaos reveals itself in flickering light, variations in brightness that happen on timescales from milliseconds to minutes, depending on the black hole's mass and the structure of the disk. These rapid variations are actually a tool for understanding black hole environments. The variability timescale sets a limit on the size of the emitting region. Something can't change brightness faster than light can cross it. If a black hole flickers on 1 second timescales, the emitting region must be smaller than 1 light second across. This lets us probe distances far too small to image directly, using time variations as a kind of telescope. Some of the most interesting variations are the quasi-periodic oscillations, frequencies that appear consistently in the X-ray light curves of accreting black holes. These might be the signature of the innermost stable circular orbit, the last place matter can circle before spiraling inward. They might reflect precession of the disk, or oscillations in its thickness, or instabilities in the magnetic fields. Different models make different predictions, and by comparing observations to theory, we're slowly figuring out what's happening in these extreme environments. It's a reminder that black holes aren't static. Even though they're often portrayed as unchanging singularities, the reality near them is dynamic and chaotic. Matter swirls and heats and collapses inward. Magnetic fields twist and snap and reconnect. The whole region pulses with energy, flickering like a candle in wind, and in that flickering we find clues to processes happening at the edge of what physics can describe. Radio telescopes can detect the faint emission from jets launched by black holes billions of light years away. Radio waves are the longest wavelength light we commonly use in astronomy, with wavelengths from millimeters to meters or more. They're produced by different processes than visible light, often by electrons spiraling in magnetic fields, a process called synchrotron radiation, and they can travel across the universe largely unimpeded by dust and gas that would block shorter wavelengths. This makes radio telescopes ideal for studying black hole jets. When relativistic particles stream away from a black hole, they spiral in the magnetic fields threading the jet, emitting radio waves that can be detected across billions of light years. Radio observations have mapped jets in extraordinary detail, revealing structure on scales from light years to hundreds of thousands of light years, the full extent of these cosmic particle beams. Some jets are straight, maintaining their direction across enormous distances. Others bend and twist, perhaps because the black hole's spin axis is precessing, or because the jet is interacting with gas in the surrounding galaxy. Some split into multiple streams, or show bright knots where particles are being reaccelerated. Each feature tells a story about the physics of the jet, about how particles and magnetic fields behave in these extreme environments, and the energy involved is staggering. A single active galactic nucleus can pump more energy into its radio-emitting lobes than the entire stellar population of its galaxy will emit over millions of years. All of it powered ultimately by gravity, by matter falling toward an event horizon, releasing its gravitational potential energy in the most efficient process nature has devised. Radio astronomy lets us see this invisible architecture, mapping the consequences of black hole feeding across scales both vast and invisible, connecting the smallest objects to the largest structures in the universe. We don't know what happens to information that falls into a black hole, a puzzle called the information paradox. In quantum mechanics, there's a fundamental principle. Information cannot be destroyed. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any other time, forward or backward. The laws of physics are reversible, deterministic in a deep sense. The information about how particles are arranged, their quantum states, their histories, all of it is preserved, encoded in the evolution of the system. But black holes seem to violate this principle. When matter falls across an event horizon, all its complex information, every detail about its quantum state, its history, the arrangement of every particle, appears to vanish. The black hole gains mass, possibly spin and charge, but nothing else. All that information seems to be lost, and destroyed behind the event horizon, where we can never access it again. This creates a profound tension between general relativity, which says the information falls into the black hole and disappears, and quantum mechanics, which says information can never be lost. Stephen Hawking spent decades working on this problem. Initially, he argued that information was indeed destroyed, that black holes were the exception to quantum mechanics rules. Later, he changed his mind, conceding that information must somehow escape, though the mechanism remained unclear. Perhaps the information is encoded on the event horizon itself, holographically preserved in subtle quantum correlations. Perhaps it's released in Hawking radiation through mechanisms we don't yet understand. Perhaps the very question reveals limitations in our theories, places where general relativity and quantum mechanics become incompatible, and we need a deeper theory, quantum gravity, to resolve the paradox. The question remains open, one of the deepest puzzles in theoretical physics, a place where our two best theories of reality fail to agree, and we're left wondering which one is right, or if perhaps they're both incomplete. The singularity at a black hole's center, where density becomes infinite, may not actually exist as predicted. At the very center of a black hole, general relativity predicts a singularity, a point where density becomes infinite, where space-time curvature becomes infinite, where the equations themselves break down and give nonsensical answers. It's not just extremely dense, it's infinitely dense, all the black hole's mass compressed to literally zero volume. Mathematically, it's a place where our description of physics stops working. Most physicists don't believe this singularity actually exists as described. Infinity appearing in your equations is usually a sign that the theory is incomplete, that it's being pushed beyond its range of validity. General relativity describes gravity beautifully at large scales, but it's a classical theory. It doesn't incorporate quantum mechanics. And at the Planck scale, distances around 10 to the minus 35 meters, quantum effects should become dominant, modifying the structure of spacetime itself. Perhaps quantum gravity, a theory we don't yet have, smooths out the singularity, replacing it with something different. Maybe it's not a point but a tiny region with finite though enormous density. Maybe it's connected to another region of space-time, though probably not in the way science fiction suggests. Maybe the singularity is replaced by something truly exotic that we haven't even imagined yet, some quantum geometry that only reveals itself when both gravity and quantum mechanics are strong. We may never know for certain. The singularity, if it exists, is hidden behind the event horizon, causally disconnected from the outside universe. We can't observe it directly, can't send probes to investigate. All we can do is theorize, build mathematical models, look for clues in the behavior of black holes we can observe, and hope that someday a theory of quantum gravity will tell us what really lies at the heart of these cosmic enigmas. Quantum mechanics suggests black holes should slowly evaporate, but we've never observed this process. Hawking radiation is one of the most beautiful predictions in theoretical physics, emerging from applying quantum field theory near black hole event horizons. The mathematics suggests that black holes should glow with a faint thermal radiation, slowly losing mass as they emit particles. But this is purely theoretical. We've never actually detected Hawking radiation from any black hole. The reason is simple: the effect is extraordinarily weak. For a stellar mass black hole, the temperature of Hawking radiation is about 10 millionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills all of space. Such a black hole would actually absorb more radiation from its surroundings than it emits, growing rather than evaporating. Only in the far future, after the universe has expanded and cooled sufficiently, would stellar mass black holes begin net evaporation. Smaller black holes would radiate more strongly. Temperature is inversely proportional to mass. A tiny black hole, if one existed, would glow hot and evaporate quickly. But we've never detected such objects, and it's not clear they could form through any natural process. So Hawking radiation remains a theoretical prediction, unverified by observation, accepted by most physicists because the mathematics is elegant and connects quantum mechanics to thermodynamics in profound ways, but still unproven. Perhaps someday we'll find a way to create or detect tiny black holes and measure their radiation. Perhaps advanced physics experiments will test the predictions in laboratory settings, or perhaps we'll simply never observe it directly and we'll have to rely on theoretical arguments and mathematical consistency. Either way, it stands as a reminder that some of physics' most beautiful ideas remain beyond our current ability to verify, predictions made by extending our theories into regimes we cannot yet directly explore. As black holes evaporate, they should get hotter, eventually exploding in a final flash of radiation. Here's a strange consequence of Hawking radiation. As a black hole loses mass through evaporation, it gets smaller, and as it gets smaller, its temperature increases. The process accelerates. A black hole doesn't fade gently away. It goes out with a bang, at least theoretically. Imagine a black hole in the distant future, after it's been slowly evaporating for countless eons. As it shrinks below a certain mass, perhaps the mass of a large mountain, it begins radiating significant energy. It heats up, glowing brighter, evaporating faster. The process runs away. In the final second of its existence, it might release as much energy as a nuclear weapon, all the remaining mass converting to radiation in a brilliant flash. Of course, this is so far in the future it's almost meaningless to contemplate. For a solar mass black hole, the evaporation timescale is around 10 to the power of 67 years. The universe is currently only 1.4 times 10 to the 10th power years old. We'd have to wait about a trillion years for stellar black holes to begin evaporating in earnest. By then, all stars will have long since died, galaxies will have dissipated. The universe will be dark and cold and empty except for these slowly radiating black holes. And they would be among the last sources of energy in the cosmos, the final places where anything happens, where radiation is emitted, where the universe generates anything that could, in principle, power processes or sustain structure, until they too evaporate, and there's nothing left but photons spreading ever farther apart in an exponentially expanding space. It's a melancholy vision of cosmic endgame, but also somehow fitting. Black holes, the ultimate endpoints of stellar evolution, would themselves be the last things to fade away. The firewall paradox asks whether the event horizon is a smooth, passable boundary or a wall of deadly radiation. Here's a more recent puzzle that emerged from thinking about black holes and quantum mechanics. For decades, physicists believed that crossing an event horizon would be smooth and unremarkable. At least for large black holes where tidal forces are gentle, you'd pass through without noticing anything special at that exact moment. This is called the equivalence principle. Locally, you can't tell the difference between being in freefall near a black hole and floating in empty space. But in 2012, several physicists proposed the firewall paradox. If Hawking radiation carries information away from the black hole to solve the information paradox, then quantum correlations require something strange. The event horizon might not be smooth at all. Instead, it could be a firewall, a region of intense radiation that would incinerate anything trying to cross it. This would violate the equivalence principle in a dramatic way. The paradox arises from trying to satisfy three seemingly reasonable requirements simultaneously: quantum mechanics rules about information, general relativity's description of smooth event horizons, and principles about how quantum entanglement works. You can satisfy any two, but not all three. Something has to give, but we're not sure what. Some physicists think the firewall doesn't exist, and the paradox reveals misunderstandings about quantum gravity. Others think firewalls are real, and event horizons are truly violent places. Still others think the whole setup shows we need a radically different understanding of how space-time works at quantum scales. The debate continues, thus one of many places where black holes force us to confront the limits of our current theories and imagine what might lie beyond them. Some theories propose that black holes could be gateways to other universes or regions of space-time. The idea of black holes as gateways or wormholes has captured imaginations for decades, in both science fiction and serious physics. The mathematics of general relativity does allow for solutions where the interior of a black hole connects to another region of space-time, either another part of our universe or conceivably a different universe entirely. These are called wormholes, or Einstein-Rosen bridges. But there's a catch, actually many catches. The simple wormhole solutions are unstable, they pinch off before anything could traverse them, or they require exotic matter with negative energy density to hold them open. The interior of a realistic black hole doesn't lead anywhere except to the singularity. Once you cross the event horizon, all paths lead inward, not to some distant exit. Time itself becomes space-like inside, and moving forward in time means moving toward the center, not toward another universe. There are more exotic proposals. Rotating black holes might have different interior geometries, perhaps with paths that avoid the singularity. Quantum effects might modify the structure in ways we don't understand. Some speculative theories suggest connections between black holes in our universe and white holes that expel matter, creating a one-way bridge. But none of this is verified, and most physicists are skeptical these configurations can exist in nature. Still, the mathematics tantalizes us. General relativity is flexible enough to allow these exotic space-time structures, even if physics seems to conspire to prevent them from actually occurring. Perhaps with quantum gravity, with a fuller understanding, we'll find that wormholes are possible after all, or perhaps we'll confirm they're purely mathematical curiosities, interesting solutions to equations that nature never implements. Either way, they remind us that space-time is stranger than we often imagine, capable of contortions and connections that challenge our everyday notions of space and distance. We don't know if the laws of physics break down inside a black hole or simply transform into something unfamiliar. What happens inside a black hole? The honest answer is, we don't know. Our equations suggest strange things. Time and space swap roles. All paths lead to the singularity. Tidal forces eventually become infinite. But do these predictions reflect reality, or do they reveal where our theories fail? General relativity works beautifully everywhere we've tested it, but it's a classical theory. It doesn't incorporate quantum mechanics, and there are strong reasons to believe quantum effects become important at the smallest scales and highest energies. Inside a black hole, approaching the singularity, we'd reach regimes where both gravitational fields and quantum effects are strong. This is the realm of quantum gravity, a theory we don't yet have. Perhaps the laws of physics don't break down at all, they just become different, thus governed by quantum gravity rather than classical general relativity. Perhaps the singularity is replaced by something with finite density, some quantum geometric structure. Perhaps time doesn't end but continues in some modified form we haven't imagined. Or perhaps the singularity is real, a place where physics genuinely breaks down, where the universe contains true discontinuities, places the laws don't reach. We may never know for certain through observation. We can't see inside event horizons, can't send probes and get data back. Our only tools are mathematics and theory, extrapolating from what we know works outside to guess what might happen inside. It's a strange position for science, studying places we can never directly observe, relying on equations and logic to explore regions permanently beyond our reach. But it's also deeply human. This desire to understand even what we cannot see, here to map the territories of the inaccessible through pure thought. Primordial black holes, formed in the early universe rather than from stars, might explain dark matter. Most black holes we know about formed from stellar collapse, created in the last moments of massive stars' lives. But there's another possibility. Black holes that formed in the very early universe, in the first fraction of a second after the Big Bang. These are called primordial black holes, and if they exist, They could be profoundly important. In the universe's first moments, matter wasn't uniformly distributed. Quantum fluctuations created denser and less dense regions. If some regions were dense enough, they could have collapsed directly into black holes. Not stellar mass objects, but potentially any mass from tiny to enormous, depending on the conditions. These primordial black holes would have formed before the first stars, ancient relics from the universe's infancy. Here's where it gets interesting. We observe that galaxies rotate faster than the visible matter alone can explain. We call the missing mass dark matter, and we know it exists through its gravitational effects. But we've never directly detected dark matter particles despite decades of searching. What if some or all of dark matter is actually primordial black holes? They'd be dark, they don't emit light, they'd have gravity, they'd affect galaxy rotation, and they'd be ancient. Distributed throughout space from the universe's earliest moments, the idea has problems. Certain mass ranges for primordial black holes are ruled out by various observations, but other ranges remain possible and searches continue. If dark matter is primordial black holes, they could vastly outnumber stellar black holes, making black holes the dominant form of mass in the universe besides ordinary matter. It would be a strange revelation that we're surrounded by ancient black holes, that they pervade every galaxy, invisible and silent, yet making up most of the mass we observe through their gravity. Some physicists wonder if our entire universe might exist inside a black hole. Here's a genuinely strange idea that emerges from the mathematics. Our entire observable universe might be the interior of a black hole that exists in some larger space-time. It sounds like science fiction, but the proposal comes from serious physics. From examining the equations and noticing similarities, the metric, the mathematical description of space-time geometry, inside a black hole has some resemblance to the metric of an expanding universe. Both involve regions where time is bounded in one direction. In a black hole, all time-like paths lead to the singularity and finite time. In our universe, all paths lead back to the Big Bang in finite time. Could these be related? Could what we call the Big Bang be actually the singularity of a black hole we're inside? The idea has several versions and faces serious obstacles. The detailed metrics don't quite match. The physics of the Big Bang and black hole singularities seem different. And there's the question of what it would even mean to say we're inside a black hole. Inside relative to what? If the entire observable universe is the interior, there's no meaningful exterior from our perspective. Still, the mathematical similarities tantalize. Some physicists pursue models where universe creation happens through black hole formation, where each black hole in our universe might spawn a new universe inside it, creating a cosmic evolutionary tree of universes budding off from black holes. It's highly speculative, probably unprovable, but it shows how deeply black holes challenge our understanding of reality, blurring boundaries between inside and outside, between the very large and the very small, as between creation and destruction. The holographic principle suggests all information about a black hole is encoded on its surface, not in its volume. In the 1990s, physicists noticed something remarkable. The entropy of a black hole, a measure of its information content, is proportional to the area of its event horizon, not its volume. For normal objects, entropy usually scales with volume. More space means more ways to arrange things, more information. But black holes are different. This led to a radical idea called the holographic principle. Perhaps all the information about a black hole's interior is encoded on its two-dimensional surface, the event horizon, much like a hologram encodes three-dimensional information on a two-dimensional film. And if this is true for black holes, maybe it's true more generally. Maybe all of three-dimensional space is itself a kind of hologram, with the true degrees of freedom living on some distant two-dimensional boundary. This idea has been formalized in certain contexts, particularly in the ADS/CFD correspondence, a relationship between gravity theories and quantum field theories that's been enormously productive in theoretical physics. It suggests a deep connection between gravity, quantum mechanics, and information theory that we're still working to fully understand. The implications are almost philosophical. If our three-dimensional reality emerges from information encoded on a two-dimensional surface, what does that mean for the nature of space? Are the extra dimensions real or emergent? Is space-time fundamental or derived from something deeper? Black holes, once again, point toward profound questions about the nature of reality itself. suggesting that our everyday experience of three-dimensional space might be only part of the story, that the universe's deepest description might look very different from the world we perceive. According to relativity, and time stops at the event horizon from the perspective of a distant observer, there's something almost poetic about this. From far away, watching something fall toward a black hole, you'd see it slow down asymptotically, approaching but never quite reaching the event horizon. Its clock compared to yours ticks slower and slower. At the event horizon itself, time dilation becomes infinite. From your perspective, time has stopped there completely. This means that, in a sense, nothing has ever actually crossed an event horizon from the perspective of an outside observer. Everything that's ever fallen toward a black hole is still there, frozen at the boundary, their images growing dimmer and redder as light struggles to escape the gravitational well, but never quite vanishing. The black hole's surface would be covered, if you could see it, with the ghostly, red-shifted images of everything that ever fell in, layered upon each other in a palimpsest of frozen time. Of course, from the perspective of what's falling in, this isn't true at all. They cross in finite time, continue inward, experience the journey. Both perspectives are valid, both are real in their own reference frames. Time isn't absolute, it's relative, malleable, different for different observers. And nowhere is this more dramatically illustrated than at an event horizon, where time itself fractures into incompatible narratives. It's a reminder that reality isn't a single story but a collection of perspectives, each valid within its own frame of reference, each seeing a different version of events, and both somehow true. The universe contains these multiplicities, these divergent timelines, and doesn't demand they reconcile into a single narrative. Time at the event horizon is both stopped and flowing, depending on who's watching, and that's not a contradiction. It's relativity. The entropy, or disorder, of a black hole is proportional to the area of its event horizon, not its volume. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a thermodynamic property related to the number of possible internal states, to information and disorder. But the formula was strange. For normal objects, entropy increases with volume. More space means more ways to arrange things. But for black holes, entropy is proportional to surface area. Specifically, the entropy is proportional to the area of the event horizon measured in Planck units, fundamental quantum units of area. Each pixel of the event horizon, roughly 1 Planck area in size, contributes 1 unit of entropy. This means black holes are the most entropic objects possible for their size, containing more disorder than anything else that could fit in the same volume. This discovery was profound. It connected thermodynamics, quantum mechanics, gravity, and information theory in unexpected ways. It suggested that black holes aren't just gravitational objects but thermodynamic systems with temperature and entropy. It hinted that space-time itself might have a quantum structure, that the event horizon isn't smooth but pixelated at the Planck scale. And it raised questions we're still pursuing. If the entropy is on the surface, is that where the information is too? Is the three-dimensional interior somehow emergent from two-dimensional surface physics? Does this apply to horizons more generally, not just black holes but cosmological horizons, boundaries of observable regions? The black hole entropy formula is deceptively simple, but it opened doors to decades of theoretical work exploring the quantum nature of gravity and space-time itself. Black holes are the darkest objects possible. They absorb all light that crosses their event horizon. By definition, black holes are perfectly black. Any light that crosses the event horizon cannot escape. It's trapped, pulled inexorably toward the singularity, adding its energy to the black hole's mass. There's no reflection, no scattering, no escape. In terms of absorbing light, black holes are perfect, achieving what laboratories can only approximate with the blackest materials. But here's the paradox. The regions around black holes can be the brightest objects in the universe. The accretion disk is heated by friction to millions of degrees, glows across the electromagnetic spectrum. Quasars powered by supermassive black holes can outshine entire galaxies. Jets launched from black hole environments can be seen across billions of light years. The darkness at the center creates the brightness around it. It's a beautiful contradiction. Ultimate darkness creating ultimate light. The black hole itself remains invisible, a shadow against the glow, but that shadow is surrounded by some of the most energetic processes in nature. The contrast is absolute. Within the event horizon, perfect blackness. Just outside, in the accretion disk and jets, brilliant radiance. The boundary between them is infinitely sharp, a line between light and darkness more absolute than anywhere else in the universe. Perhaps there's a metaphor here, though physics doesn't traffic in metaphors. Still, it's striking how darkness and light coexist at black holes, how they define each other, how the absence at the centre creates the presence around it. The universe seems to enjoy these juxtapositions, these studies in contrasts, placing its darkest and brightest places right next to each other, separated by a boundary both infinitely thin and infinitely consequential. A spinning black hole could theoretically allow closed time-like curves, paths through space-time that loop back to their starting point in time. Inside the ergosphere of a maximally spinning black hole, the mathematics of general relativity allows for something deeply strange. Closed time-like curves. These are paths through space-time that loop back on themselves not just spatially but temporally. Follow one of these curves, and you'd return to the same point in space and time where you started. In other words, time travel. The possibility emerges from the way rotating black holes warp space-time. The extreme rotation drags space-time around so severely that light cones, the regions of space-time you can reach from a given point, tip over, creating paths that curve back in time. Mathematically, these solutions exist. Whether they exist physically is another question. Most physicists are skeptical that closed time-like curves are actually possible. They create logical paradoxes. What if you travelled back and prevented your past self from starting the journey? Nature seems to avoid such contradictions. Perhaps quantum effects prohibit closed time-like curves. Perhaps you can't actually extract them from physically realistic black holes. Perhaps some cosmic censorship prevents their formation, but the mathematics allows them, which is remarkable. General relativity, our best theory of gravity and space-time, contains within it the possibility of time travel, at least near rotating black holes. Whether nature implements this possibility or finds ways to forbid it remains unclear. It's another example of how black holes push our theories to their limits, revealing possibilities both fascinating and troubling, making us wonder what else might be lurking in the equations, what other strange features of reality our mathematics predicts but nature may or may not permit. The maximum spin rate for a black hole is when its event horizon rotates at the speed of light. Black holes can spin, but there's a limit. As a black hole's rotation increases, its event horizon shrinks and distorts, becoming oblate like a squashed sphere. The rotation rate is measured by a dimensionless parameter, usually denoted A, ranging from 0, not rotating, to 1, maximum rotation. At E equals 1, the event horizon is rotating at the speed of light. This maximum spin is called the extremal limit. You can't spin a black hole faster than this. The mathematics suggests that trying to would eliminate the event horizon entirely, creating a naked singularity, which cosmic censorship hypothesizes doesn't happen in nature. So there's a speed limit on black hole rotation just as there's a speed limit on motion through space. Most black holes probably aren't spinning at the extremal limit. As they accrete matter or merge with other black holes, they gain or lose angular momentum. But some might approach it, spinning at 95% or 99% of the maximum rate. These fast-spinning black holes are the most efficient at powering jets through the Penrose process, extracting rotational energy to accelerate particles to relativistic speeds. The spin rate also affects the black hole structure. A maximally spinning black hole has its innermost stable circular orbit right at the event horizon, whereas a non-spinning black hole has this orbit 3 times farther out. This means matter can orbit closer to an extremal black hole before falling in, releasing more energy, heating to higher temperatures. The fastest spinning black holes are thus the most powerful engines, squeezing the maximum energy from infalling matter, approaching the theoretical limits of how efficiently mass can be converted to radiated energy. Charged black holes could theoretically repel other charges, but we've never found one in nature. Einstein's equations allow for black holes with electric charge, creating what's called a Reissner-Nordström black hole if it's not rotating, or a Kerr-Newman black hole if it is. The mathematics is well understood, the solutions are exact. Charged black holes would have interesting properties. Like charged particles would be repelled, the event horizon structure would be different, potentially with an inner and outer horizon. But we've never detected a charged black hole in nature. And there's a good reason: charge neutrality. If a black hole had net positive charge, it would attract electrons and repel protons from its surroundings. The electrons would fall in, neutralizing the charge. Similarly, a negatively charged black hole would attract protons. Any charge would quickly be neutralized by attracting opposite charges from the surrounding space. So charged black holes remain theoretical curiosities, solutions to equations that nature appears not to implement, at least not in any stable way. They're studied because they help us understand the mathematics of black holes more generally, because the techniques used to analyze them apply to more realistic cases, and because they represent the full generality of the solutions to Einstein's equations. It's a reminder that not everything mathematically possible is physically realized. The universe has its preferences, its rules beyond the equations. Mathematics gives us a space of possibilities, but nature chooses among them, selecting solutions that are stable, that can actually form through physical processes, that survive in realistic environments. Charged black holes, elegant as they are mathematically, appear to be roads not taken, possibilities that remain only in the imagination of theorists. The smallest possible black hole would have a mass comparable to the Planck mass, about 22 micrograms. There's a fundamental scale in physics called the Planck scale, where quantum gravity effects become important. The Planck mass is about 22 micrograms, tiny by everyday standards but enormous for a quantum particle. If you could compress this much mass into a Planck length, about 10 to the minus 35 meters, you'd have the smallest possible black hole. At this scale, our understanding completely breaks down. The Planck length is so small that space-time itself might become quantum and fuzzy, no longer describable by smooth geometry. The Planck time is so short that our notion of causality might not apply. Classical general relativity predicts these mini black holes would exist, but quantum effects almost certainly dominate their behavior. Such tiny black holes would be incredibly hot. Their Hawking temperature would be around 10 to the power of 32 Kelvin, unimaginably energetic. They'd evaporate almost instantly, existing for only about 10 to the power of minus 43 seconds, before radiating away all their mass. We've never seen such objects. And it's not clear any natural process could create them, at least not in the current universe. But they might have formed in the very early universe when conditions were more extreme. They might appear in high-energy particle collisions, though experiments at the Large Hadron Collider have found no evidence of them. They represent the boundary where our theories meet, where gravity and quantum mechanics both matter equally, where we need quantum gravity to make predictions. And we don't have that theory yet. So Planck mass black holes remain hypothetical, markers of the frontier beyond which current physics cannot reliably venture. Some theoretical black holes could exist in higher dimensions, behaving in ways impossible in our three-dimensional space. String theory and other approaches to quantum gravity often propose that space-time has more than the 4 dimensions we experience: 3 of space, 1 of time. These extra dimensions might be compactified, curled up so small we don't notice them, but their existence would change how gravity works and how black holes behave. In higher dimensions, black holes can have different properties. Their event horizons might not be spherical, but have more complex shapes. They might radiate Hawking radiation more efficiently, evaporating faster than 4-dimensional black holes. They might be easier to create in particle collisions, which is one reason physicists looked for them at the LHC. Higher dimensional black holes also exhibit instabilities that don't exist in our familiar dimensions. Some configurations can become unstable, deforming and potentially splitting into smaller black holes or radiating away. The mathematics becomes rich and complex, revealing possibilities that seem exotic from our 3-dimensional perspective. These ideas remain theoretical, tested only through mathematics rather than observation. But they help physicists explore how dimensionality affects physics, how the number of spatial dimensions shapes the behavior of gravity and matter. Even if the extra dimensions don't exist, studying higher dimensional black holes teaches us about the structure of theories, about what's universal across dimensions and what's specific to our 4-dimensional space-time. It's exploration through imagination and mathematics, but using black holes as probes to understand the possible architectures of reality. A naked singularity, a singularity without any event horizon, would allow us to observe infinite density directly. General relativity's equations allow for a disturbing possibility, a singularity not hidden behind an event horizon. This would be a naked singularity, visible to the outside universe, a place where density and space-time curvature become infinite, but not cloaked by the cosmic censorship of an event horizon. If naked singularities existed, they'd be deeply problematic. Singularities are places where our physics breaks down, where equations give infinite or undefined results. Event horizons protect us from this breakdown, ensuring that whatever strange physics happens at the singularity remains causally disconnected from the rest of the universe. But a naked singularity would be visible, its effects reaching us, potentially allowing influences from regions where physics as we know it fails. Roger Penrose proposed the cosmic censorship hypothesis to address this. He suggested that nature forbids naked singularities, that any singularity formed through realistic physical processes will always be clothed by an event horizon. For decades, this remained a conjecture, neither proven nor disproven. Physicists have found contrived scenarios where naked singularities might form, but these usually require fine-tuned initial conditions unlikely to occur naturally. Recent work suggests cosmic censorship might hold in most realistic cases, but could be violated in certain exotic situations. The question remains open, one of general relativity's unanswered questions. Whether the universe truly prohibits naked singularities, or merely makes them extremely rare, we don't yet know. But the fact that the equations allow them, that we must make an additional hypothesis to exclude them, suggests our theory is still incomplete, still pointing toward deeper truths about how nature regulates its own extremes. Virtual black holes might constantly pop in and out of existence at quantum scales throughout all of space. Quantum mechanics tells us that empty space isn't truly empty. It's filled with quantum fluctuations, particle-antiparticle pairs that pop into existence and annihilate almost immediately, energy borrowed from uncertainty and quickly repaid. These fluctuations are real. They create measurable effects like the Casimir force between conducting plates. If quantum fluctuations can create particles, might they also create black holes? At the Planck scale, where quantum effects and gravity are both strong, space-time itself might fluctuate, creating tiny regions of extreme curvature, virtual black holes, that exist briefly before evaporating. These wouldn't be classical black holes but quantum objects, subject to the uncertainty principle, neither quite there nor quite not there. If virtual black holes exist, they'd affect how particles propagate through space, slightly modifying forces and interactions at very short distances. They might contribute to vacuum energy, possibly even to the cosmological constant that drives cosmic acceleration. They'd be part of the quantum foam, a hypothetical structure where space-time becomes grainy and fluctuating at the smaller scales. But this is all highly speculative. We have no direct evidence for quantum foam or virtual black holes. They emerge from trying to apply quantum reasoning to gravity, but without a full theory of quantum gravity, we can't make reliable predictions. Still, the idea is tantalizing, that reality at its deepest level is far from the smooth, continuous space-time of classical relativity, that everywhere, at every point, space-time is bubbling and fluctuating with transient structures that include tiny, short-lived black holes. If true, it would mean black holes aren't just cosmic objects but fundamental features of space-time itself, present everywhere, always, hidden below the scale we can currently observe. The idea of an object whose gravity prevents light from escaping was proposed by John Michell in 1783. More than 2 centuries before we photographed black holes, before Einstein developed relativity, even before we understood what light truly was, an English clergyman named John Michell imagined dark stars. In 1783, he considered what would happen if a star were massive and compact enough that its escape velocity exceeded the speed of light. Light, which Michell thought of as corpuscles, tiny particles, would be unable to escape such an object's gravity. His reasoning was based on Newtonian physics and an incomplete understanding of light's nature. He didn't know about space-time curvature or event horizons. He simply followed the mathematics of gravity and motion to a logical conclusion, and remarkably, he arrived at something resembling the modern concept of black holes over a century before we had the physics to properly describe them. This mom. Michell's work was largely forgotten, rediscovered only in historical retrospectives after black holes became accepted in modern physics. But there's something beautiful about his prescient speculation, his willingness to follow ideas to their logical extremes. He showed that human imagination, armed with mathematics, can sometimes glimpse truths about nature before we have the full framework to understand them. The universe hints at its secrets through multiple pathways, and sometimes those pathways lead brilliant minds to correct conclusions even from incomplete premises. Michel's dark stars were wrong in detail but right in spirit, a testament to the power of mathematical reasoning to reveal reality's hidden possibilities. Karl Schwarzschild found the first exact solution to Einstein's equations describing black holes while serving in World War I. In 1915, Einstein published his general theory of relativity, a set of complex equations describing how mass and energy curve space-time. Einstein himself solved them only in approximations. Finding exact solutions seemed impossibly difficult. But within weeks, a German physicist named Karl Schwarzschild found the first exact solution while serving in the German army on the Russian front during World War I. Schwarzschild's solution described the space-time geometry around a spherical, non-rotating mass. It revealed the structure we now recognize as a black hole, an event horizon at what's called the Schwarzschild radius, a singularity at the center. He sent his calculations to Einstein in a letter from the war front in December 1915, just months after Relativity's publication. Einstein was astonished. He'd thought finding exact solutions would be nearly impossible, yet Schwarzschild had done it under the most difficult circumstances imaginable, whilst doing theoretical physics between military duties in an active war zone. Tragically, Schwarzschild never saw the full impact of his work. He contracted a rare autoimmune disease on the Russian front and died in May 1916, just 42 years old, months after his breakthrough. His name lives on in the Schwarzschild radius, the size of the event horizon for a non-rotating black hole. It's a reminder that scientific insight can emerge anywhere, under any conditions. As der Stuhl. When brilliant minds engage with profound questions, and it's a poignant story, a mind capable of unlocking the universe's secrets, extinguished by the violence and disease of the war, leaving behind an equation that would outlive empires and illuminate the darkest objects in the cosmos. The term black hole was popularized by physicist John Wheeler, who had a gift for memorable phrases. Language shapes how we think, and John Wheeler understood this better than most physicists. Throughout his career, he coined or popularized terms that made abstract physics concepts accessible and memorable. Black hole is perhaps his most famous contribution, though he didn't invent it. He popularized it starting in 1967, giving official sanction to a term that had been floating around informally. Before Wheeler embraced black hole, physicists used awkward phrases: gravitationally completely collapsed object, frozen star, Schwarzschild singularity. These were descriptive but cumbersome, hard to say, harder to remember. Black hole was simple, evocative, almost poetic. It captured something essential about these objects: their darkness, their emptiness, the sense of something missing from space. Wheeler also gave us wormhole, adapting an earlier term to describe hypothetical tunnels through space-time. He coined it from bit, suggesting that information might be more fundamental than physical reality. He helped develop the concept of quantum foam. He had an instinct for phrases that stuck, that captured complex ideas in ways people could hold in their minds. Perhaps he understood that science isn't just about equations and data, it's also about narratives and concepts, about building mental models that let us think about the invisible and the abstract. A good name can make the difference between an idea that remains obscure and one that captures imaginations. Black hole did exactly that, transforming a mathematical curiosity into something vivid enough to appear in popular culture, serious enough to describe some of the universe's most important objects. Wheeler knew that words matter, that the right phrase can open minds to possibilities they might otherwise overlook. In the 1970s, Stephen Hawking bet physicist Kip Thorne that black holes didn't exist, and later conceded. Scientific wagers have a long tradition, and one of the most famous involves Stephen Hawking and Kip Thorne. In 1974, Hawking bet Thorne that Cygnus X1, a strong X-ray source and prime black hole candidate, didn't actually contain a black hole. This seems strange. Well, Hawking had spent years developing black hole physics. Why bet against them? Hawking later explained it was a form of insurance. His life's work focused on black holes. If they turned out not to exist, at least he'd win a bet, a subscription to Private Eye magazine. But if they did exist, well, his work would be vindicated and he'd gladly pay Thorne's prize, a subscription to Penthouse, which Thorne, with characteristic humour, claimed was for the articles. Over the years, evidence accumulated. Observations of Cygnus DX-1 grew more precise. The invisible companion's mass was determined more accurately, its compactness confirmed. By 1990, Hawking conceded. He reportedly broke into Thorne's office when Thorne wasn't there and signed the bet agreement conceding defeat. The story is charming for several reasons. It shows scientists maintaining good humour about fundamental questions, willing to be proven wrong, treating uncertainty as an opportunity for friendly wagers rather than dogmatic positions. It also reflects a genuine moment of uncertainty in the 1970s, when black holes were still theoretical objects, observational evidence was ambiguous, and even experts weren't entirely sure they existed. That era of uncertainty passed, replaced by confidence built on decades of observations. Now we don't just know black holes exist, we've photographed them, detected their collisions, is measured their properties. Hawking lost his bet, but won the deeper satisfaction of knowing his theoretical work described real objects in the cosmos. The movie Interstellar featured the most scientifically accurate depiction of a black hole ever created for film. In 2014, the science fiction film Interstellar showed audiences a black hole rendered with unprecedented scientific accuracy. The filmmakers worked with physicist Kip Thorne to create visualizations based on actual general relativity calculations. The result, a black hole named Gargantua, looked different from the artistic renderings people expected. The accretion disk didn't just surround the black hole in a simple ring. Due to gravitational lensing, you could see the disk both above and below the black hole. The light paths bent so severely that the far side of the disk wrapped around, becoming visible above and below the black hole's shadow. One side of the disk appeared brighter due to relativistic beaming, matter moving toward the camera at a significant fraction of light speed. Creating these accurate visualizations required developing new rendering software and performing relativistic ray tracing calculations, following light paths through curved space-time. The process generated new insights for physicists, leading to published papers. Visual effects software created for entertainment purposes advanced our scientific understanding of how light behaves near rotating black holes. The film showed millions of people what a black hole actually looks like according to our best physics. When the Event Horizon Telescope released the first real black hole image in 2019, it resembled Gargantua in important ways: the glowing ring, the dark shadow, the asymmetry. Art had anticipated reality, or rather, art informed by rigorous physics had predicted what reality would reveal. It's a beautiful example of how science and creativity can reinforce each other, how accurate science can enhance rather than constrain artistic vision, producing images both scientifically correct and aesthetically stunning. Ancient philosophers contemplated whether space could contain voids or regions of absolute nothingness. Long before modern physics, humans wondered about emptiness and void, and ancient Greek philosophers debated whether true nothingness could exist. Aristotle argued that nature abhors a vacuum, that empty space was impossible. Democritus and the atomists countered that void must exist between atoms, that matter and emptiness were both fundamental. These weren't questions about black holes. The ancients lacked the physics to conceive of such objects, but they were grappling with related ideas. Can space be truly empty? What is the nature of absence? Can something be defined by what it's not rather than what it is? These philosophical questions prefigured scientific ones about vacuum, space-time, and eventually black holes. In a sense, black holes are the ultimate voids, regions where matter has disappeared behind an event horizon, where space-time itself is so warped that normal notions of inside become ambiguous. They're not voids in the Aristotelian sense. They contain mass and curvature, but they represent absence, darkness, regions removed from causal contact with the rest of the universe. The ancient debates about void and matter, absence and presence, infinity and finitude. These weren't just philosophical exercises, They were early attempts to understand fundamental aspects of reality, using logic and reasoning in the absence of experimental data. Modern physics has given us tools those ancient thinkers lacked, but the questions they ask remain relevant. What is the nature of empty space? What does it mean for something to not exist in a particular region? How do we define objects by their boundaries rather than their contents? Black holes make these ancient philosophical questions concrete, giving them physical manifestations we can study and measure. The 2020 Nobel Prize in Physics was awarded for theoretical predictions and observational discoveries of black holes. In October 2020, the Nobel Committee recognized black hole research with its highest honor. The prize was split between Roger Penrose for theoretical discoveries and Reinhard Genzel and Andrea Ghez for observational work. It was a moment that acknowledged how far black hole physics had come, from speculation to established science deserving of Nobel recognition. Penrose's contribution came in 1965 when he proved mathematically that singularities must form under general conditions in gravitational collapse, not just in idealized symmetric cases, but in realistic scenarios. His work showed that singularities weren't mathematical artifacts, but genuine predictions of general relativity, unavoidable consequences of the theory. Genzel and Ghez led teams that independently observed stars orbiting the center of our galaxy for decades, tracking their motion with increasing precision. Their work proved that Sagittarius, a star, contained about 4 million solar masses in a region smaller than our solar system, requirements that only a black hole could satisfy. They turned the galactic center into a laboratory for testing gravity under extreme conditions. The award represented more than individual achievements. It recognized an entire field that had matured from theoretical speculation in the 1960s to observational science with hard data, images, gravitational wave detections. Black holes had gone from hypothetical curiosities to central objects in astrophysics, fundamental to understanding galaxy evolution, stellar death, the nature of space-time. The Nobel Prize was an acknowledgement that these once exotic objects were now established parts of cosmic architecture, worthy of our highest scientific honors. Black holes have become metaphors in popular culture for irreversible loss, inescapable situations, and the unknown. Beyond physics, black holes have entered our cultural consciousness as symbols and metaphors. We speak of falling into a black hole when we lose time to internet browsing or deep research. We call inescapable situations black holes of bureaucracy or debt. We use them to represent the unknowable, the mysterious, the places where normal rules don't apply. These metaphorical uses capture something real about black holes, their boundaries, their irreversibility, their mystery. The event horizon is genuinely a point of no return. What lies inside is genuinely unknowable from outside. They genuinely represent extremes where familiar physics breaks down. The metaphors work because they're grounded in actual properties, but the metaphors also simplify and sometimes distort. Cultural black holes are often portrayed as active threats, cosmic vacuum cleaners that reach out to grab things. Real black holes are more passive, their gravity working like any other massive objects at a distance. The popular image of black holes as all-consuming destroyers misses their subtlety, their role as recyclers of matter and energy, their place as fundamental structures in cosmic evolution. Still, the metaphorical power of black holes speaks to something important. Science creates concepts that transcend their technical origins, becoming part of how we think about the world. Black holes give us language for certain types of experiences and situations. They populate our imagination, appearing in art, literature, film. They've become cultural objects as much as scientific ones, meaning different things to different people while retaining their scientific reality. Perhaps that's as it should be. The universe's most extreme objects becoming symbols for our own extremes of experience, knowledge, and uncertainty. Some religious and philosophical traditions have drawn parallels between black holes and concepts of cosmic recycling or rebirth. Across cultures and traditions, humans have contemplated cycles of creation and destruction, the idea that endings enable new beginnings. Some Eastern philosophies speak of cosmic cycles where universes are born, evolve, and dissolve, only to be reborn. Various traditions imagine death not as termination but as transformation, matter returning to source before emerging renewed. Black holes, in some interpretations, resonate with these ideas. Matter enters them and disappears from our observable universe, but energy is released in the process. Black hole mergers create gravitational waves that spread through space. Evaporating black holes return their mass energy to radiation. Nothing is truly lost. It's transformed, redistributed, changed in form but conserved in fundamental ways. Some speculative physics proposals suggest black holes might even seed new universes through quantum processes, though this remains highly theoretical. If true, it would create a kind of cosmic evolutionary process where black holes become wombs for new spacetimes, destruction enabling creation, endings containing beginnings. These parallels shouldn't be pushed too far. Science and spirituality operate in different domains with different methods and goals, but there's something compelling about how black holes embody transformation and mystery, how they challenge our notions of permanence and loss. Different traditions find different meanings in them, and perhaps that's natural. The universe is large enough to support multiple interpretations, multiple ways of finding meaning in its structures. Black holes, sitting at the intersection of knowledge and mystery, invite contemplation from both scientific and philosophical perspectives, each enriching our understanding in its own way. Science fiction has explored black holes as power sources, weapons, time machines, and gateways for centuries. Actually, that's not quite right. Black holes only entered science fiction in the mid-20th century, after they emerged from theoretical physics. But in the decades since, they've become staples of speculative fiction, serving almost every narrative purpose imaginable. They've been energy sources for advanced civilizations, extracting power through Penrose processes or Hawking radiation. They've been weapons, dropped into enemy star systems or used to destroy fleets. They've been time machines. They're extreme time dilation, or exotic interior geometries enabling journeys to the past or future. They've been gateways to other universes, other dimensions, other points in space. Some of these ideas have basis in real physics. Black holes genuinely could serve as power sources. Time dilation near them genuinely could enable forward time travel. Others are more speculative or outright impossible, but they're narratively useful, giving authors tools to explore ideas about time, space, causality, the nature of reality itself. Science fiction often anticipates or inspires science, asking what-if questions that sometimes lead to genuine research. And sometimes science fiction helps us think about implications of discoveries, exploring consequences before they're technologically relevant. Black holes in fiction serve both purposes. They're exotic enough to enable fantastical stories, while grounded enough in real physics to maintain plausibility. And perhaps fiction does something else too. It makes black holes familiar, gives them narrative context, lets people encounter these cosmic extremes in stories before encountering them in scientific papers. When real discoveries happen, when we photograph black holes or detect their collisions, the public isn't starting from zero. Science fiction has prepared the ground, made black holes part of our cultural vocabulary, helped us imagine what scientific discoveries might reveal. Art and science together, different languages describing the same astonishing universe. The smallest stellar black holes have event horizons about 30 kilometers across, roughly the size of a small city. 30 kilometers. That's about the distance you might drive in 20 minutes on a highway, the width of a small metropolitan area. And yet within that space, compressed into a sphere that's small, sits the entire mass of a star perhaps 10 or 20 times more massive than our Sun. Sees every atom that once made up that star, all its hydrogen and helium, the heavier elements forged in its core, all of it collapsed down to a point, surrounded by an event horizon just 30 kilometers across. It's difficult to truly grasp this scale. We're used to massive objects being large. Planets are thousands of kilometers across, stars are millions. But black holes invert this expectation. The more massive they are per unit volume, the smaller they become in a sense. All that matter compressed beyond atoms, beyond nuclei, into densities that make the centers of stars seem empty by comparison. If you could somehow stand on the surface of a neutron star, the precursor to a stellar black hole, you'd experience gravity about 1 billion times stronger than Earth's. But that's still not a black hole. Push just a bit further, add just a bit more mass or compress just a bit more, and suddenly the gravity becomes strong enough that light cannot escape. The event horizon forms at about 30 kilometers for a 10 solar mass black hole. And inside that boundary, space-time itself is so warped that all paths lead inward. 30 kilometers, a distance you could walk in a few hours on Earth. But around a black hole, it's the boundary between the observable universe and oblivion, between the region where physics makes predictions we can test, and the region where we can only theorize. Oh, such a small distance to mark such an absolute division in the nature of reality. The largest known supermassive black holes have event horizons bigger than our entire solar system. At the opposite extreme are the giants, supermassive black holes containing tens of billions of solar masses, their event horizons spanning hundreds of billions of kilometers. If you placed one of these monsters where our Sun sits, its event horizon would extend far beyond the orbit of Pluto, engulfing all the planets, the asteroid belt, the Kuiper belt, reaching into the realm where the Sun's influence fades and interstellar space begins. TON 618, one of the most massive black holes we know, contains roughly 66 billion solar masses. Its event horizon has a diameter of about 390 billion kilometers, over 2,600 times the Earth-Sun distance. Light takes more than 54 hours to cross from one side of its event horizon to the other. It's not just a black hole, it's a black region. A shadow that could swallow solar systems whole. These supermassive black holes are old, ancient perhaps, possibly forming when the universe was young and growing through billions of years of feeding and mergers. They sit at the centers of massive galaxies, gravitational anchors around which hundreds of billions of stars orbit, and yet, despite their enormous mass, they still represent a tiny fraction of their host galaxy's total mass, perhaps a few tenths of a percent. The scale is almost incomprehensible. We struggle to visualize even our solar system's size, the vast distances between planets. Now imagine all of that space filled by a single object's event horizon, a boundary beyond which nothing returns. These giants reshape space-time across volumes that dwarf planetary systems, their gravity influencing not just nearby stars but the entire galactic core, their presence shaping the evolution of galaxies themselves. They remind us that the universe creates structures at every scale, from the subatomic to the cosmic, and that black holes span nearly that entire range. If you could compress Earth to the size of a marble, it would become a black hole. Here's a thought experiment. Take all of Earth, every mountain and ocean, every city and forest, every person and every atom, and compress it. Not to the density of ordinary matter, not even to the density of neutron stars, but smaller still. Compress it until all 6 septillion kilograms of our planet fits within a sphere about 9 millimeters across, about the size of a marble you might find in a child's game. At that point, Earth would become a black hole. The event horizon would form at about 9 millimeters radius, 18 millimeters across. Inside that tiny sphere would be everything that makes up our world, compressed beyond comprehension into a singularity. The Schwarzschild radius, the size of the event horizon for any given mass, depends only on the mass, not on what that mass is made of or how it's arranged. For Earth's mass, it's 9 millimeters. This tells us something profound. Becoming a black hole isn't about mass alone, it's about density. Earth is far too diffuse to be a black hole at its current size. The Sun, despite being 330,000 times more massive than Earth, also isn't a black hole. It would need to be compressed to about 3 kilometers radius. Only by achieving extreme density, by crushing matter down to scales where quantum effects and gravity both become paramount, does a black hole form. And this compression isn't something we could do with any technology. It's not a matter of applying enough pressure. At the densities required, matter itself resists in ways we can only partially understand, through quantum mechanical effects. It is degeneracy pressure, ultimately forces we don't fully comprehend. Only gravity itself in the collapse of massive stars can achieve this compression. The universe creates black holes not through effort, but through inevitability, when gravity simply has no opposition left. The density required to form a black hole actually decreases as mass increases. Here's a counterintuitive fact. Larger black holes are less dense on average than smaller ones. A stellar mass black hole, if you calculated its average density by dividing its mass by the volume inside its event horizon, would be incredibly dense, billions of times denser than atomic nuclei. But a supermassive black hole containing billions of solar masses would have an average density similar to water, or even less. This seems paradoxical until you remember that the event horizon radius grows linearly with mass, while volume grows as the cube of radius. Double the mass and you double the radius, but increase the volume 8-fold. The average density, mass divided by volume, decreases as mass increases. Of course, average density is somewhat misleading. All the mass is still at the singularity, infinitely dense. The event horizon is just empty curved space-time. But if you imagine spreading the mass uniformly throughout the volume enclosed by the event horizon, which isn't what actually happens, you'd find that for the largest supermassive black holes, this hypothetical average density is surprisingly low. This means that, in principle, you could be inside the event horizon of a sufficiently large black hole and not immediately notice anything wrong. The tidal forces would be gentle, the average density around you, if matter were distributed uniformly, which it isn't, would be no worse than water. Only by trying to escape, only by finding that all possible paths lead inward, would you realize your predicament. And only by continuing inward, approaching the singularity where the real density becomes extreme, would conditions become lethal. Large black holes offer a gentler approach to oblivion, at least at first, a strange sort of mercy from the universe's most extreme objects. Stellar black holes are extraordinarily rare. Perhaps 1 in every 1,000 stars is massive enough to become one. When you look up at the night sky, you're seeing thousands of stars with your naked eyes, millions through telescopes. The vast majority will never become black holes. They're too small, born with insufficient mass to collapse all the way to an event horizon. They'll end their lives as white dwarfs or neutron stars, dense remnants but not black holes. Only stars born with at least 20 times the Sun's mass, sometimes the threshold is quoted as 25 or 30, depending on composition and mass loss, will collapse into black holes. These massive stars are rare. The initial mass function, which describes how many stars form at different masses, strongly favours smaller stars. For every star massive enough to become a black hole, there might be 1,000 smaller stars that won't. And yet, even being rare, as black holes accumulate over cosmic time, stars have been forming and dying for billions of years. The massive ones burn through their fuel quickly. A 20 solar mass star might live only 10 million years compared to the Sun's 10 billion. They've had time to form, evolve, and collapse. Generations of massive stars have already completed their life cycles. So while black holes are rare compared to stars, there are still many of them. In the Milky Way alone, perhaps 100 million stellar mass black holes, scattered through the spiral arms and the halo, invisible unless they happen to be accreting matter or orbiting visible companions. They're the rare outcomes, the extreme cases, but in a galaxy of hundreds of billions of stars, even rare outcomes occur millions of times. The universe is large enough that even its most extreme possibilities become commonplace on cosmic scales. The total number of stellar mass black holes in the observable universe likely exceeds 40 quintillion. Quintillion. That's a number with 18 zeros. 40 quintillion. Try to imagine it. It's more than the number of grains of sand on all Earth's beaches. It's comparable to the number of insects that have ever lived on Earth. And it's a conservative estimate for how many stellar mass black holes exist in the observable universe. The calculation goes something like this. The observable universe contains perhaps 1 trillion galaxies, each containing on average 100 billion stars or more. Over cosmic history, some fraction, perhaps a few percent, of those stars were massive enough to become black holes. Not all of those massive stars have died yet, but many have, especially in older galaxies. Run the numbers and you get tens of quintillions of black holes. These black holes are spread across incomprehensible distances. The observable universe spans 93 billion light-years. Black holes are scattered through that entire volume, in galaxies near and far, most of them completely invisible, detectable only if they happen to be accreting matter, or if we get lucky and they lens light from background sources. And this estimate includes only stellar mass black holes. Add in supermassive and intermediate mass black holes, and the count grows, though supermassive ones are limited, perhaps one per large galaxy. Still, it's staggering. The universe has created tens of quintillions of these objects, each one a warping of space-time, a region where matter has collapsed into profound curvature. They're everywhere, distributed throughout cosmic history and cosmic space, far more common than we might naively think, yet still so sparse that the average distance between them spans light years. The universe is both full of black holes and mostly empty of them, another of the strange contradictions that come from working at cosmic scales. Despite their fearsome reputation, black holes occupy a tiny fraction of space. Most of the universe is vast emptiness. It's easy to focus on black holes and forget about everything else, to imagine them as ubiquitous threats filling the cosmos. But the reality is quite different. Space is overwhelmingly empty, and black holes, despite their numbers, will occupy almost none of it. Consider, even in dense regions of galaxies where stars are relatively close together, the average distance between stars is several light years. Black holes are rarer than stars and similarly distributed. The nearest known black hole to Earth is about 1,500 light-years away. In our cosmic neighbourhood, say, within 100 light-years of Earth, there might be no black holes at all, and even near a black hole most of space is safe. The gravitational influence extends far, yes, but it follows the same inverse square law as any mass. Orbit far enough away, and the black hole's gravity is gentle, indistinguishable from any other object of similar mass. Only close to the event horizon do the exotic effects emerge. The universe is a study in emptiness with occasional islands of matter and energy. Galaxies cluster together, but are separated by millions of light-years of near void. Within galaxies, and stars are separated by light-years of space. Within star systems, planets orbit through mostly empty space, and black holes, despite being the densest objects we know, are so rare and so localized that they barely make a dent in the universe's overall emptiness. Perhaps this is reassuring. For all the dangers black holes represent, for all their extreme physics, you have to actively seek them out to encounter one. The universe doesn't fill itself with hazards. It creates extremes but places them sparingly, leaving vast volumes of gentle, navigable space between them. We're not surrounded by black holes. We're surrounded by light-years of near-empty space, with occasional stars, even more occasional black holes, and countless opportunities for existence untroubled by extreme gravity. The escape velocity at a black hole's event horizon equals the speed of light, 299,792 kilometers per second. Escape velocity is the speed you'd need to escape from a gravitational field without further propulsion, the speed where kinetic energy exactly balances gravitational potential energy. On Earth, escape velocity is about 11 kilometers per second. Launch something at that speed and it'll escape Earth's gravity, coasting into space even without additional thrust. For more massive or more compact objects, escape velocity increases. On the Sun's surface, 618 kilometers per second. On a white dwarf, thousands of kilometers per second. On a neutron star, approaching half the speed of light. And at a black hole's event horizon, escape velocity reaches exactly the speed of light, 299,792 kilometers per second, the cosmic speed limit, the fastest speed anything can travel. This is why nothing escapes from inside the event horizon. Not even light, travelling at the maximum possible speed, has sufficient velocity to escape. The event horizon marks the boundary where escape velocity equals light speed, where the requirement to leave exceeds what physics permits. It's not that objects lack powerful enough rockets. No amount of thrust can accelerate you past light speed. The speed of light is absolute, and at the event horizon, escape requires the impossible. This also means that just outside the event horizon, escape is possible, but requires velocities approaching light speed, energy expenditures that are practically impossible for massive objects. There's a region near the event horizon where technically you could escape, but practically you can't, where the energy costs are so prohibitive that escape becomes effectively impossible, even before you cross the point of no return. The black hole's grip tightens gradually, then absolutely. The event horizon marking the transition from nearly impossible to actually impossible, from physics that permits escape to geometry that forbids it. A teaspoon of matter from a black hole's accretion disk could outweigh Mount Everest. This fact needs careful qualification. The accretion disk itself, the swirling gas and dust around a black hole, isn't particularly dense in most regions. It's hot plasma, actually quite diffuse. But near the innermost stable orbit, and just before matter spirals across the event horizon, conditions become extreme. pressure and density reach levels unimaginable elsewhere. In the very inner regions of the disk around a stellar mass black hole, densities can approach or exceed those in neutron stars, about 1 billion tons per cubic centimetre. A teaspoon of this matter would contain roughly the mass of Mount Everest, all compressed into a volume you could hold in your hand. If your hand could somehow withstand the temperature of millions of degrees and the pressures that would instantly vaporize any ordinary matter, of course, you couldn't actually scoop out a teaspoon of this material. The moment you removed it from its environment, it would explosively decompress and cool, expanding rapidly and releasing enormous energy. The density exists only because of the intense gravity and pressure of the black hole environment. Remove that support and the matter would revert to more normal densities almost instantaneously. But the fact remains, near black holes, matter achieves densities comparable to the densest objects in the universe. Atoms are crushed beyond their normal structure. Electron clouds are stripped away. Nuclei pack together with minimal space between them. The ordinary matter we're familiar with, where atoms are mostly empty space, becomes something else entirely, compressed, exotic, existing in states we can barely replicate in our most extreme laboratory experiments. It's matter at the edge of what's possible before complete collapse to a singularity, a preview of the extreme physics that governs black holes themselves. The gravitational pull of Sagittarius A is strong enough to accelerate stars to 2% the speed of light. The stars orbiting closest to our galaxy's central black hole move at speeds that seem impossible for objects so massive. S2, the star we discussed earlier, reaches velocities around 3% the speed of light at its closest approach, about 9,000 kilometers per second. Other stars in even tighter orbits move even faster, some reaching perhaps 5% of light speed or more. For comparison, Earth orbits the Sun at 30 kilometers per second, already fast enough to circle Earth's equator in 20 minutes. But the stars near Sagittarius A* move hundreds of times faster, crossing distances in seconds that light takes minutes to traverse. At these speeds, relativistic effects become measurable. Time dilation is detectable, mass effectively increases. The rules of Newtonian physics give way to Einstein's relativity. These orbital velocities tell us about the black hole's mass. The faster the orbits, the more massive the central object must be to hold them in their paths. By measuring stellar velocities and orbital periods, astronomers calculated that Sagittarius A* contains about 4 million solar masses, all concentrated in a region smaller than Mercury's orbit. No other explanation fits the observations. Only a supermassive black hole could confine stars to such tight, fast orbits. And these stars are laboratories, testing general relativity in gravitational fields hundreds of times stronger than anywhere else we can observe directly. Each orbit provides data, each closest approach offers measurements. We watch them dance around the invisible mass at our galaxy's heart, and in their motion we read the fundamental rules of gravity and space-time, confirmed every time their positions match the predictions of equations written a century ago by a physicist who never imagined we'd have the tools to test his theory in such extreme conditions. Next-generation gravitational wave detectors will hear black hole mergers from the universe's first billion years. The current generation of gravitational wave detectors, LIGO, Virgo, Kagra, has opened a new window on the universe, detecting dozens of black hole mergers, but they have limitations. They're most sensitive to stellar mass black holes merging relatively nearby within a few billion light years. More distant mergers, or mergers of more massive black holes that emit gravitational waves at lower frequencies, remain beyond their reach. But new detectors are coming. The Einstein telescope, proposed for construction in Europe, would be 10 times more sensitive than current detectors. LIGO India will add another observatory to the network, and most ambitiously, the Laser Interferometer Space Antenna, LISA, would consist of 3 spacecraft flying in formation millions of kilometers apart, forming a triangular detector in space, sensitive to lower frequency gravitational waves that Earth-based detectors can't access. These future instruments will detect black holes from the universe's earliest epochs, mergers that occurred when the first galaxies were forming, when stars were just beginning to create the heavy elements, when supermassive black holes were growing from their mysterious seeds. We'll hear the gravitational waves that have been travelling for over 13 billion years, messages from the cosmic dawn, telling us about black holes that formed when the universe was young. Each detection will be a story about cosmic history, about how black holes formed and evolved in environments very different from today's universe. We'll learn whether supermassive black holes grew primarily through mergers or accretion. We'll discover if intermediate mass black holes were common in the early universe. We'll map the population of black holes across cosmic time, watching how they changed as the universe aged and evolved. The gravitational wave sky will become as rich and detailed as the electromagnetic sky, giving us a complete census of black holes throughout space and time. Future space-based telescopes might image the photon rings around black holes in unprecedented detail. The Event Horizon Telescope achieved something remarkable, imaging black holes' shadows from Earth's surface. But the resolution is limited by the size of our planet. Even using the entire Earth as a telescope, we can barely resolve the largest nearby black holes. To see smaller black holes or study larger ones in greater detail, we need bigger telescopes, and the only way to build a bigger telescope is to go to space. Proposals exist for space-based interferometric arrays, multiple satellites flying in formation, their observations combined to create effective telescope apertures larger than Earth. Such arrays could operate at different wavelengths, potentially imaging black holes in optical or infrared light in addition to radio waves. They could resolve features on event horizon scales for many more black holes, not just the handful we can currently image. With higher resolution, we could test general relativity even more precisely. We could measure black hole spins with greater accuracy. We could watch the dynamics of accretion disks on timescales of minutes or hours, seeing how turbulence and magnetic fields shape the flow of matter. We could image the photon ring structure in detail, potentially detecting the multiple images created by light orbiting the black hole several times before reaching us. These observations would probe space-time curvature in the most extreme accessible conditions, testing whether Einstein's equations hold in gravitational fields billions of times stronger than anything in our solar system. Any deviation from predictions would be revolutionary, potentially revealing new physics, quantum gravity effects, or fundamental modifications to our understanding of space-time. And even if general relativity passes every test, which seems likely, we'll gain deeper understanding of how these extreme objects actually behave, moving from theoretical models to detailed observations of reality's most extreme laboratories. We may soon detect intermediate mass black holes directly through gravitational waves from their mergers. Intermediate mass black holes, those containing hundreds to thousands of solar masses, have long been the missing middle children of black hole families. We know stellar mass black holes form from collapsing stars. We know supermassive black holes inhabit galactic centers. But intermediate mass black holes, if they exist in significant numbers, have remained elusive. Gravitational wave detectors are beginning to change this. They've already detected a few candidates, black holes in the 100 solar mass range that might qualify as the lowest end of intermediate mass. As detectors improve in sensitivity, they'll access more of this mass range, potentially detecting mergers involving black holes of thousands of solar masses. These detections will answer important questions. How do intermediate mass black holes form? Are they products of hierarchical mergers in dense star clusters? Where stellar mass black holes combine repeatedly? Are they direct collapse black holes formed in the early universe? Do they represent a bridge between stellar mass and supermassive black holes, perhaps serving as seeds that grow into the giants at galactic centers? The intermediate mass range is crucial for understanding black hole formation across cosmic history. Finding these objects and measuring their properties, masses, spins, merger rates, will fill a critical gap in our knowledge. It will connect stellar physics to galactic evolution, linking the deaths of individual massive stars to the growth of supermassive black holes, and it will reveal whether the universe creates black holes at all possible masses, or whether there are gaps, forbidden ranges where black holes cannot exist for reasons we don't yet understand. The answers are encoded in gravitational waves, waiting for detectors sensitive enough to hear them. Quantum gravity experiments might reveal how information escapes from evaporating black holes, solving the information paradox. The information paradox, whether information is truly lost in black holes or somehow preserved, has troubled physicists for decades. Hawking initially argued information was destroyed, violating quantum mechanics. Later he conceded it must be preserved somehow, but the mechanism remained mysterious. The paradox sits at the intersection of quantum mechanics and general relativity, precisely where we need a theory of quantum gravity to resolve it. Recent theoretical work suggests possible solutions. Some proposals involve quantum entanglement, between the black hole's interior and the Hawking radiation it emits, with information gradually encoded in subtle correlations in the radiation. Others suggest that the event horizon itself has quantum structure, perhaps storing information holographically on its surface and releasing it as the black hole evaporates. We might be approaching testable predictions. While we can't observe Hawking radiation from astrophysical black holes, they're too cold, future experiments might create analog systems that mimic black hole physics in laboratory conditions. Sonic black holes in flowing fluids, optical black holes in light, i.e. quantum simulations on supercomputers. These could test aspects of Hawking radiation and information preservation in controlled settings. If information is preserved, if it escapes in Hawking radiation through quantum effects we're beginning to understand, it would resolve one of physics' deepest paradoxes. It would show that quantum mechanics holds even in the most extreme gravitational fields, that the universe keeps a record of everything, that no information is ever truly lost. And it would give us profound insights into quantum gravity, showing how gravity and quantum mechanics merge at the deepest level, how space-time itself emerges from or connects to quantum information. The answer might reshape our understanding of reality's fundamental nature. Advanced civilizations might use black holes as ultimate energy sources, extracting power from their spin and mass. Imagine a civilization millions of years more advanced than ours, one that's outlived its stars. That exists in a universe growing dark and cold. Where would they find energy? One answer: black holes. Through the Penrose process, a civilization could extract up to 29% of a rotating black hole's mass energy, harvesting rotational energy by dropping matter into the ergosphere and recovering energetic particles that escape. Alternatively, they might build a Dyson sphere around a black hole, not to capture starlight but to harvest radiation from the accretion disk. As matter spirals inward, it releases enormous energy, potentially providing power for trillions of years if the black hole is large enough and the fuel supply adequate. The efficiency would exceed any other power source. Better than fusion, better than antimatter, limited only by how much matter could be fed into the black hole. In the far future, as the universe expands and cools, black holes might become the primary remaining energy sources. Hawking radiation from evaporating black holes would be among the last sources of free energy in the cosmos. A sufficiently advanced civilization might position itself near black holes, using them as beacons of negentropy in an otherwise maximally entropic universe. These scenarios are speculative, bordering on science fiction, but they're grounded in real physics, in the genuine possibility of extracting work from black holes, rotational and mass energy. Whether any civilization will ever achieve this technology we can't know, but the universe permits it, at least in principle, and black holes could theoretically sustain technological civilizations for timescales that dwarf the current age of the cosmos. In the longest view, black holes might be not endpoints but way stations, sources of power that outlast stars, persisting into the deep future of an aging universe. We might discover primordial black holes through their gravitational effects on visible matter and light. If primordial black holes exist, formed in the early universe rather than from stellar collapse, they could be scattered throughout space, invisible wanderers drifting through galaxies and voids. How would we detect them? They wouldn't emit light, they might not have accretion disks, but they would have gravity, and that gravity would reveal them. One method is gravitational microlensing. When a massive object passes between us and a distant star, its gravity bends the star's light, temporarily brightening it in a characteristic way. Searches for microlensing have detected brown dwarfs and planets this way. Primordial black holes would create similar signatures, brief brightenings as they drift across our line of sight to background stars. Another method involves their effects on galaxies and structure formation. If primordial black holes make up a significant fraction of dark matter, they would influence how galaxies rotate, how matter clusters, how cosmic structures evolved. Precise measurements of these effects could reveal their presence indirectly, even if we never see individual primordial black holes. And if primordial black holes are small enough, less than a certain mass threshold, they would be evaporating now through Hawking radiation. The final explosions would release gamma rays and other particles we could potentially detect. Searches for such signals continue, looking for flashes that might mark the death of ancient black holes formed in the Big Bang's first moments. Each non-detection constrains the possibilities, ruling out certain mass ranges and abundances, but viable windows remain. primordial black holes might still be out there, hidden in the dark matter halo around galaxies. Ancient relics from the universe's birth, waiting to be discovered through patient observation and clever inference from their gravitational fingerprints. Improved simulations of black hole mergers will help us understand what happens when event horizons collide. When two black holes merge, their event horizons, previously separate surfaces in space-time, come together and fuse. This happens in moments, too quickly for any external process to interact with. The merger creates a wildly distorted event horizon that settles into a sphere through a process called ringdown, emitting gravitational waves with characteristic frequencies as the new black hole oscillates like a struck bell. Simulating this process requires solving Einstein's equations numerically, following how curved space-time evolves as the black holes spiral together. For decades this was impossible. The equations are nonlinear, coupled, incredibly difficult to solve computationally. Breakthroughs in the mid-2000s finally allowed stable simulations, and since then they've improved dramatically in accuracy and detail. Future simulations will model more complex scenarios, black holes with different masses and spins, mergers that happen at different angles, systems with surrounding matter and magnetic fields. These simulations will predict gravitational wave signals with precision, allowing us to test whether observations match theoretical expectations, whether general relativity accurately describes the merger process in all its complexity. And they'll help us understand the moment of merger itself. What happens to the two singularities as they approach? Do they touch and combine, or does quantum gravity intervene somehow? What happens to the information content? The classical equations suggest the singularities merge, but quantum effects might modify this picture. Simulations can explore different models, making predictions about what gravitational wave observation should reveal if certain quantum gravity theories are correct. The merger of black holes isn't just a spectacular cosmic event, it's a probe of physics at the boundary between relativity and quantum mechanics, where our current theories strain and perhaps break down. Future observations might reveal whether black holes truly have no hair or hide subtle features we haven't detected yet. The no-hair theorem states that black holes are characterized by only three numbers: mass, spin, and charge. All other information, the details of what fell in, the black hole's formation history, is supposedly erased. But this theorem rests on assumptions: that general relativity is exactly correct, that black holes are truly isolated, that quantum effects don't modify the picture. Future observations might detect deviations from the no-hair theorem. For instance, gravitational waves from black hole mergers encode information about the merging object's properties. If black holes have additional features beyond mass and spin, perhaps imprints from quantum gravity, perhaps structures related to how they formed, these might appear as small deviations in the gravitational wave signal. Similarly, improved imaging of black hole shadows might reveal asymmetries or features not predicted by simple models. Perhaps the event horizon has structure at quantum scales. Perhaps black holes formed through different mechanisms have subtly different properties even at the same mass and spin. These differences might be tiny, but future instruments might be sensitive enough to detect them. Finding deviations would be revolutionary. It would mean black holes are more complex than we thought, that they retain memory of their formation or quantum structure, that the no-hair theorem is approximate rather than exact. It would point toward quantum gravity effects observable in astrophysical black holes, giving us clues about how to unify relativity and quantum mechanics. But if observations continue confirming the no-hair theorem, if black holes remain as simple as the theorem predicts, that's also profound. It would mean nature really does erase information in this way, or at least hides it so deeply that even our most sensitive instruments can't detect the complexity. Either outcome, confirming or violating no-hair, teaches us something fundamental about how the universe works at its most extreme. In the unimaginably distant future, black holes will be the last remaining structures in the universe before they too evaporate into radiation. Let's look far ahead, beyond anything we can meaningfully plan for or even properly imagine. In about 1 trillion years, the last stars will exhaust their fuel and die. The universe will contain no more fusion, no more starlight, only the fading embers of white dwarfs and the cold remnants of stellar death. But black holes will remain, patient and dark, the last massive structures in an increasingly empty cosmos. Over the following eons, even these remnants will fade. White dwarfs will cool to black dwarfs, dark and cold. Planets will either fall into stars or be ejected from their systems through gravitational interactions, while galaxies themselves will evaporate as stars are flung into intergalactic space or spiral into the central black holes. After perhaps 10 to the 20 years, most matter will have either fallen into black holes or been ejected into the void, and then the black holes will evaporate, the smallest ones first over timescales of 10 to the power of 67 years or more. Larger ones will take longer. Supermassive black holes might persist for 10 to the power of 100 years, a googol of years, a timescale so vast it mocks our attempts to comprehend it. But eventually, through Hawking radiation, they will all evaporate, returning their mass to photons and particles spreading through an exponentially expanding space. After the last black hole evaporates, the universe will contain only radiation, growing more dilute as space expands, temperature approaching absolute zero. This is heat death, maximum entropy, no free energy remaining to power processes or sustain structure. It's a state the universe seems destined for. Barring physics we don't yet know, and black holes will have been the last holdouts, the final islands of structure in an ocean of increasing entropy, burning slowly through Hawking radiation until they too surrender to the inexorable march toward equilibrium. Black holes represent not just endpoints for individual stars, but waypoints on the universe's own journey from birth to heat death, making them both tombstones and time capsules of cosmic evolution. We've journeyed through 100 facts about black holes, from their discovery to their distant future, from their quantum properties to their cosmic roles. And perhaps what emerges most clearly is this: black holes are not separate from the universe's story. They are integral chapters in it, marking transitions between different cosmic eras, embodying physics at its extremes, connecting the very small to the very large. They begin as endpoints, the final state of massive stars that have exhausted their fusion fuel and collapse beyond any force's ability to resist. In this sense, they're tombstones, markers of stellar death, monuments to gravity's ultimate victory. But they're also agents of transformation. The energy released in their formation, as supernovae, as mergers, enriches the cosmos with heavy elements, seeds new generations of stars and planets, shapes the evolution of galaxies. They sit at galactic centers, possibly influencing galaxy formation, definitely affecting how galaxies evolve, their feeding and feedback shaping stellar populations across billions of years. They merge and create gravitational waves that ripple through space-time, carrying information about cosmic history. They might even be the last sources of energy in the far future, the final places where entropy can be locally reduced, where work can be done, before the universe settles into its final heat death. And they probe the boundaries of knowledge, forcing us to confront the limits of our theories, to imagine what lies beyond relativity and quantum mechanics, to wonder about the nature of information and reality and time itself. Every question we ask about black holes leads to deeper questions. Every answer reveals new mysteries, and perhaps that's as it should be. The universe's most extreme objects should challenge us most deeply, should resist easy explanation, should demand our best theories and still hold secrets beyond them. So as you drift towards sleep, perhaps think of black holes not as cosmic monsters, but as cosmic teachers, showing us through their very existence how reality works at its boundaries, how matter and energy and space-time itself behave when pushed to extremes. They're beautiful in their mathematical elegance, profound in their implications, and endlessly fascinating in their refusal to give up all their secrets. From the first stars to the universe's last gasp, black holes will be there, witnesses to cosmic history, participants in cosmic evolution, mysteries that invite our curiosity and reward our investigation with glimpses of the sublime. And that brings us to the end of our journey through these 100 facts about black holes, these remarkable objects that sit at the intersection of everything we know and everything we're still trying to understand. We've wandered through quite a lot together, haven't we? From event horizons to information paradoxes, from stellar collapse to the distant future of the cosmos. We've contemplated objects that bend space-time until light cannot escape, that compress stars into points, that might harbour secrets about the nature of reality itself. And through it all, I hope you found not fear or anxiety, but wonder, the kind of gentle curiosity that makes the universe feel less like a cold, mechanical place and more like an endlessly fascinating story still being written. Black holes remind us that the cosmos is stranger and more beautiful than our everyday experience suggests. Time isn't constant. Space isn't flat. Matter doesn't always behave the way we expect, and yet through mathematics and observation, through patient investigation and creative thinking, we've learned to understand these extremes, to make friends with the incomprehensible, to find patterns and meaning in what initially seems like pure mystery. Perhaps what's most remarkable is that we can understand them at all, that equations written on paper or calculated in computers actually describe reality billions of light years away, that the same laws governing a falling apple also govern black holes containing billions of solar masses. The universe speaks in mathematics, and we've learned, slowly and imperfectly but genuinely, to speak some of that language back. If you're still awake, that's wonderful. I hope these ideas have given you something to contemplate, some new perspective on the cosmos we inhabit. And if you're drifting off, if these words are becoming softer and the ideas hazier, that's perfect too. Let them wash over you like gentle waves. The universe will still be here tomorrow, still mysterious, still beautiful, still waiting for curious minds to explore its depths. Thank you for joining me on this journey through the darkest and most fascinating objects in the cosmos. Until we meet again for another quiet exploration, rest well. The black holes will keep their vigil, patient and eternal, while you sleep beneath the same stars that feed them, in a universe vast enough to contain both you and them, both life and void, both light and darkness. Good night.